Nikita,
Hello, sir.
can you hear me?
Yes, perfect.
Thank
I
you.
can hear you. I can see you.
Good, good.
Hi, Aaron.
Tell me. You are all very brave people.
Bye.
Why is that? What makes us brave?
Taking all these responsibilities.
Oh, I see.
5-minute chairman makes me nervous.
So we'll wait for a little bit time. People are just coming in.
Yeah.
Yes. So it's 9 o'clock. Should we start? Professor Nagaraju, are you there?
Yeah.
Okay.
First is Pratap. Is that right?
Yeah. Okay, so very warm welcome to day 2 of LDMAT. So yesterday we had a very interesting day with large number of exciting talks, and we heard a lot about graphene physics and very exciting physics which is going on in thin films and their novel electronic properties which emerges out of them. So we also hope for a very exciting day today. So I would like to invite Professor Nagarajan to chair the first session. He's Professor Emeritus at UMDA CBS. He superannuated from TIFR and he's very well known for his famous borocarbide superconductor discovery. So over to you, sir.
Good morning. Thanks, Sangeeta. You made an interesting statement a few seconds ago. Yesterday, when Dr. Mittal chaired the first session, he mentioned that he feels like attending a refresher course with all the kind of excitement which was presented yesterday. I feel as if it's a fresh course I am attending and not a refresher course. Thanks to Sangeeta and Padmanabh Rai for bringing me up to date in this exciting field of material science. Today's speaker, in fact, before I even go to that, I want to see a strange coincidence. I feel as if it's a family function. Can you hear me?
Yeah.
Yes,
Hello?
absolutely.
Little louder will be better.
Okay. I feel it's a family function because both the speakers, one of the organizers, Dr. Sangeeta, and myself belong to the same origin, TIFR. Obviously, I'm very, very happy to chair this session. The first speaker of this session, Dr. Pratap Ray Chaudhary, was a student of TIFR. Of course, he is still in TIFR as a professor now. He had so much work. He had a lab in front of my lab and behind my lab. Even at that time, he used to make such wonderful research. I had predicted to my colleague that he would be a star. He did not disappoint me. He got Bhatnagar Prasad, Shanti Swarup Bhatnagar Award, elected as Fellow of Indian Academy of Sciences, elected a member of Low Temperature Commission of International Union of Pure and Applied Physics. And I am sure soon he will have many more awards. I am very happy to chair the session in which my dear Pratap is going to give a keynote lecture. Now, his research area is investigation of superconducting magnetism in bulk and thin films through a variety of tunneling spectroscopy. If you go to his lab, you will see it crammed with all things, majority of them made by himself, and of course, crammed with a lot of liquid helium containers. I think I now will invite Pratap to give his keynote lecture, please.
Okay, thank you, Arun, for your kind introduction.
I told you 45 minutes talk with 5 minutes discussion. And I also want to appreciate the organizers for specifically making this 5 minutes gap for the question session. Thank you.
Okay. Thank you, Arun, for your introduction. And I thank the organizers for giving me this opportunity. Unfortunately, this conference is parallel with another conference where I am the convener, so I couldn't attend as much as I wanted to. But nevertheless, I attended mostly the junior talks yesterday, and I found that several of the junior speakers gave excellent talks. So I hope I can live up to that. Okay, so what I will be talking today is on something very new, which is zero-point fluctuation of vortices in superconducting amorphous emoji thin film. So before I start, these are all my students, postdocs, and scientific staff. The experimental work that I will be showing you is entirely done in TIFR. So all experimental data that I will be showing you is from my lab, taken by my students. And for theory, however, we collaborate with whoever is the most appropriate. So we have collaborators all over the world. We have very active collaboration with theorists in Sapienza University in Italy. However, the main topic of this talk, the zero-point fluctuation, we have collaborated with Shubhi Sajdev in Harvard. All right, so let me start with the prelude. Okay, so the work that I will be telling you about has just been accepted. You can look at this paper if you are interested, but I will be covering a lot of the basics as well. And those basics are in this publication. Okay, let me start with the prelude. What is zero-point fluctuation? Now, we all know from quantum mechanics that if you put, let's say, a particle in a confining potential, then this particle cannot go exactly at the energy bottom of the potential. So, for example, if you have a harmonic potential like this, then the lowest energy a particle can be in this harmonic potential is not the bottom here, as you will classically imagine, but it is slightly higher. So this harmonic oscillator problem we all have solved in quantum mechanics, and you know that you have this discrete energy level and the lowest energy level.
Was there a change in program of today's? My God.
Is there a... Am I audible?
Yeah, you're audible. That's fine. Continue.
All right. So the lowest energy level has an energy which is half h cross omega above the bottom of the potential. This energy is called the zero-point energy. And now what this means is that even in its ground state, the particle is not static, but it's actually oscillating. And the amplitude of this oscillation you can estimate by equating this half omega square a square, the total energy of an oscillator with h cross omega. And this will tell you that the amplitude of this zero-point energy will be given by h cross by m omega to the power half. The important point is that the amplitude of this zero-point fluctuation, which is this delta A here, goes inversely as the root of the mass, which means that if you have lighter particle, you have a larger zero-point fluctuation. It also means that if you go to absolute zero temperature, the particle will not be at rest. It will still have an oscillation of this amplitude. This is the minimum oscillation amplitude that the particle can have in a harmonic potential. Now, why am I telling all this? The reason I am telling all this is that this has a profound consequence in condensed matter physics. If you take a solid, then in a solid, every atom is in a confining potential created by its neighboring atoms. And therefore, these atoms are actually moving in this potential, they are oscillating in this potential. This potential is approximately harmonic. So now it will have a zero-point motion. And if you have very light atoms like helium, then this zero-point motion can be large enough that down to T equal to 0, the liquid does not solidify. We know that normally liquids, when you cool, they solidify, but this is the pressure temperature phase diagram of liquid helium, and you can see that helium remains a liquid down to T equal to 0 for this kind of pressure, which includes atmospheric pressure here at 1 bar. And this happens because the 0 point fluctuation is so large that the solid cannot stabilize. However, helium is, and this kind of a liquid which remains down to T equal to 0 because of this quantum effect are called quantum fluid. Now, the question is, we know that helium is a quantum fluid, but are there other solid or liquid systems where we can see ramification of this 0 point fluctuation? This is what is the topic of this talk today. So the system that I will be talking about, our solid, is not a real solid here. It's a solid which is made of vortices in a type 2 superconductor. So let me quickly tell you what are vortices in a type 2 superconductor. We all know that certain materials, when you cool them below a certain temperature, the resistance goes to 0. And this is what is called superconductivity. I don't need to introduce superconductivity here. Now, superconductivity has many interesting properties. And one of the interesting property of superconductor is its magnetic property. Now, there is a class of superconductors which are called type 2 superconductors, where if you apply a magnetic field beyond a certain value, which we call HC1, you have the magnetic field that enters in the sample, but it doesn't enter homogeneously. It enters in the form of these flux tubes that you see here. And each of these flux tubes, they carry a quantum of flux, which is given by this expression H by 2E. So you can see that this is a universal number, and this is the flux quantum, which is a universal constant. So now when you have a flux that enters at some point in the superconductor, it locally destroys the superconductivity there. So if you look from the top, what you will see is wherever you have this flux tube, which are often called vortices, you have the central region which has become normal, which is no longer superconducting. So this is the normal metal core. This is surrounded by circulating supercurrent, which produces this magnetic field and sustains the flux. Now, these flux tubes, they actually are like bar magnets which have the same polarity, and therefore they repel each other. And due to this repulsion, when you have many flux tubes, you have applied a significant amount of magnetic field and you have many flux tubes, this repulsion arranges them into a hexagonal structure. And this is what is called the Abrikosov vortex lattice. Now this lattice is actually like a solid, except that now my solid is made of these flux tubes. It is not made of atoms. And this is the solid that I will be studying today. Now I am showing you nice images like this. How can you capture such an image? Our tool, our toy to capture this image is what is known as a scanning tunneling microscope. So the way it operates is like this. You have, suppose, the superconductor here. You bring a normal metal tip very close to it. And you bring it so close within a nanometer so that you can have quantum mechanical tunneling of electron from the superconductor to this normal metal tip. Now, suppose I take this tip here at this point A, where now before that, let me just mention, so now if I measure this tunneling conductance as a function of voltage, then if this is a superconductor and this is a normal metal tip, the tunneling conductance as a function of voltage will look like this blue line. So these are called the coherence peaks of the superconductor, and this is the superconducting gap. This tunneling conductance is proportional to the density of states, and in the gap, the density of states is 0. On the other hand, if I go to the normal state, if I have a normal metal, which is, for example, the superconductor above its transition temperature, then this tunneling conductance as a function of voltage will be flat, like this red line. So now I have these vortices here by applying magnetic field. If I bring the tip here, then I will be tunneling from a normal metal to a superconductor because I have so I don't have a vortex beneath it. But if I go on the top of a vortex, I have told you that at the center of the vortex, you have this normal core. So here I will be tunneling from a normal metal tip into the normal core. So therefore, in one case, if I stay at a bias voltage, which is, let's say, close to this coherence peak, which I have shown in the arrow here, here I will measure a large conductance, here I will measure a smaller conductance. So I take this tip and I raster over the sample, I take the conductance map, and this minima of the conductance map shows where the location of the vortices are. So this I am showing a small area, I can do it over a large area, and this is how we capture the image of the vortex line. Okay, this is just an advertisement slide. This is our millikelvin scanning tunneling microscope. I would like to emphasize that this is a homemade machine. So if you are interested in building a scanning tunneling microscope of this kind, we can also apply a magnetic field of 9 Tesla. You can look at this paper or you can contact us or whatever. Okay. So the superconductor that we will be using today is molybdenum germanium thin film, as I have already mentioned. This is an amorphous system. So if you do a TEM, then there is a TEM image where you see that there is no order of the atoms. And if you measure its superconducting properties, then it's a conventional superconductor. So in that way, it's an unremarkable superconductor. It has a PC of 7 Kelvin. It has a fairly large upper critical field exceeding 10 Tesla. Now the superconducting gap follows the BCS behavior. The superfluid density also follows the BCS behavior. Now, there is one thing that you have to remember. If I had taken, let's say, a bulk single crystal and produced the crystal vortex lattice by applying magnetic field, then the vortices are long like this. And these vortices are not exactly rigid, so they can intertwine, like you can see here. They are more like spaghetti. So this is what is called a three-dimensional vortex lattice. But what I will be using today is a thin film. And this thin film is 20 nanometer thick. And over this length, these vortices cannot bend. So these vortices now will look like these points. And when they arrange, this will be effectively like a two-dimensional solid. Now, why is the two-dimension important? Two-dimension is important because, as you know, normally, if you take a solid and you heat it, then it melts. Or, for example, if you take ice and you apply pressure on it, it melts. And it melts through a first order phase transition. This is what we read in textbooks. This is true for a large variety of solids and all three-dimensional solids. But for a two-dimensional solid, it was shown in the 70s by Berezinski, Kosterlitz, and Thouless that there is an alternate route of melting that is possible. The alternate route of melting is this. From a solid, here, a two-dimensional solid, you can produce dislocations and get into a state which is called a hexatic. Now, this hexatic is in between a solid and a liquid. The hexatic state is a very interesting state because here the atoms do not have positional order, the atoms or the vortices in our case, but you have orientational order. So you have preferred direction. So the hexatic is a fluid state, but this fluid cannot flow with equal mobility in all directions. It flows preferentially along the principal axis of the crystal. And then this hexatic, subsequently, if you keep on increasing temperature, it will eventually melt by these dislocations unbinding into disclinations, and here you will produce isotropic liquid. Okay, so this one of our initial goal in this project was to actually see if we can find a hexatic fluid made of vortices. And amorphous molybdenum germanium was a very good candidate for this, for two reasons. The first reason is that it was amorphous, so there is no underlying crystal lattice that will interfere with the symmetry of the vortex lattice by coupling with the vortex lattice symmetry. The second reason is that this was a material which has extremely low pinning. So any superconductor will have some amount of defects, and these defects prevents the motion of these vortices, so that these vortices can no longer rearrange the way they want to under their mutual interactions. Now, this kind of pinning, this is what is called pinning of vortices, and pinning of vortices prevents from the system attaining its true equilibrium state. Now, we have characterized pinning through many means. I will not go into the details, but what we realize is that the pinning here is actually 5 to 6 orders of magnitude smaller than typically, let's say, an IBM film or a high temperature superconducting film. Now, one of the things for those who are slightly familiar with superconductivity, you can see here that the field cool and zero field cool state of the sample exactly overlap with each other. In fact, the points are the field cool at the points at the zero field cool state and the lines at the field cool state. Unless I tell you, you think that it's just the same data plotted twice. And they exactly overlap with each other, and this is actually a signature that the vortices, no matter what you do, are going to their equilibrium configuration. So we have effectively very, very low pinning. All right, now with this, we will start looking at the vortices. Now, molybdenum germanium is not a new material. It has been known for many years, and yet no one ever looked at the vortices using a scanning tunneling microscope, which is one of the most powerful tools to look at the vortex lattice order. And the reason for that is that this material gets oxidized very fast. You form an oxide layer on the surface, and after that, you cannot get STM data which are neat enough to rely on them. The way we avoided this problem is a very interesting method. We grow these films by pulse laser deposition. You can see our chamber here. And then without taking them out in air, these films are transferred into this ultra-high vacuum suitcase. This ultra-high vacuum suitcase, then you decouple from the chamber, you take it to your scanning tunneling microscope, couple it here. The scanning tunneling microscope chamber is anyway at high vacuum, and you directly load this sample inside your STM. So it has never seen air. The surface is pristine. And with this, you start doing STM on this sample. So this data are at 2 Kelvin. I am initially at low field. Here you have a vortex solid, a hexagonal solid made of vortices. Then you start forming dislocations. This is what is the hexatic fluid state. And then eventually at high field, this hexatic fluid state becomes an isotropic liquid. Now I'll show you some movies which demonstrates this very clearly. So let me take this data first at 1 Kelvin, and what I'm showing you here is I am taking the image of this small area of the vortex lattice, and I am taking successive images every 10 minutes. And I am tracking the motion of every vortex. So I am connecting the position on the nth frame of the vortex with the position in the n+1th frame by arrows. So you can see here in the solid state, these vortices are just moving a little bit about their mean position. So that is what you expect. There is no large translational motion. So I have to tell you here, there is no applied drive. I am not pushing the vortices. This is, if you want, the thermal motion, which you know in the case of liquid gives rise to Brownian motion. Now this is for the solid state. Now staying at 2 Kelvin, I increase the magnetic field. And this is at 55 kilohertz. And what do you see here? Here you see that the vortices have started moving and moving quite significantly, but they are moving along a preferential direction. And this direction is actually one of the principal lattice directions of the underlying vortex solid. So this is what is the hexatic, and in this hexatic now, the vortices are mobile, but they are not mobile like in a Brownian motion where the whole movement is random. They are moving in preferential direction. You increase the magnetic field further. So remember, here increasing magnetic field is same as increasing density. So in the case of ice, whatever you do by increasing pressure on it, here magnetic field plays the same role. Now, if I go to at 85 kilohertz state, you can see that I have this hexatic fluid has become a regular isotropic liquid. So now the motion is truly random, and this is what you study in when you study Brownian motion in school. Okay, so we were very happy that we can actually capture the hexatic state from the images. But then we also wanted to look at what is its ramification in transport. So first I will show you, I told you that the hexatic state is different from the isotropic liquid because it has orientational order. Since we have these images, we can calculate this orientational order from this angle of these nearest neighbor bonds. And if you calculate this metric of orientational order, you will, from the images that I showed you, you will see that you have a finite orientational order in the hexatic, and then around 70 kilohertz state that orientational order crashes, and this is where you get the isotropic liquid. You have already seen that here the motion becomes completely random. Now there is also signatures of these transitions in transport. Ultimately, I am dealing with a superconductor. So I have to look at what happens in electrical transport. In electrical transport, what happens is interesting. In the vortex solid, you cannot move one atom in a solid, or you cannot move one vortex inside a vortex solid. You have to move the entire solid, and that costs a lot of energy. So therefore, in the vortex solid, if you try to pass a current and measure the resistance, you get zero resistance. But now you enter the hexatic fluid. In a fluid state, you can move each of the vortices independently. So therefore, even with a very small force, you can move some of the vortices, and this motion of the vortices produces electrical resistance. So you see that the resistance starts appearing in the hexatic. But though resistance appears, the vortices cannot move very much. They are sort of constant movement because they can move only in certain direction. When you have the transition to the isotropic liquid, suddenly the vortices are free to move in any direction they want, and therefore you have again a sudden increase, large increase in the resistance. So this is the signature of the hexatic to isotropic liquid transition. So you can see that both these phase transitions from vortex solid to hexatic fluid and hexatic fluid to isotropic liquid, you can now, after you have identified them from real space images, you can also track them using electrical transport, resistance measurement. So we do many of these resistance measurement, and you produce this phase diagram. In this phase diagram, the intriguing thing is this. that you look at these fluids. I have a fluid, vortex fluid, that's not so remarkable. What is remarkable is that I am going to low temperature, and here I am plotted up to 300 millikelvin, 0.3 Kelvin. And yet I have such a large range of magnetic field where I see a fluid state. So it appears that the fluid state is not solidifying when I am going to low temperature. Normally you would expect a fluid to solidify unless it's a quantum fluid like helium. Okay, now of course you cannot go to t equal to 0, and we cannot rule out that the true source that this liquid will possibly solidify at an even lower temperature. But we, at this point, we decided to investigate on whether there are signatures of 0-point fluctuation. So this brings me to the main topic that I will cover in the next 10 or 15 minutes. So Aaron, tell me when I have 10 minutes or so. Okay. There is a question. Devjani, I will take your question at the end. Is that okay? All right. So now, so far I have just looked at the configuration of vortices. So instead of the configuration of vortices, now let us look at the structure of individual vortices. So I will zoom into one vortex and see what the structure of the vortex is. Let me first explain what you expect. So this first I am showing you a niobium diselenide single crystal. So there is a different system. A niobium diselenide single crystal is one of the most canonical superconductors. So it's a superconductor that doesn't have any peculiarity. So I want to first show you what you expect in a normal run out of the mill situation, and then I will show you what you see here. So I go along this line here, and I keep on taking this conductance as a function of bias voltage spectra at small intervals. So when I am away from the vortex center, you can see I have a coherence peak and a nice gap here, as I expect in a superconductor. When I am at the center of the vortex, now at the center of the vortex is a normal metal. So I should have expected something that is completely flat. What I get instead, as you see here, is a peak. And that I show it more prominently here, this curve B, where you see a peak here. Now, what is this peak? This peak is called the Caroly-Dogen-Matricorn peak, and this happens because you are confining the electron within the normal electron. So you have a normal metal which is very narrow at the center, and you are confining these normal metals in 2 dimensions in the X and Y direction. In the Z direction, it's free to move within, let's say, few nanometer. So now when you are confining like this in a 2-dimensional box, you know that the ground state wave function of a 2-dimensional box will be somewhat like this. And this, if you want, is the mod square of the wave function of the particle in a box. That is why you get this peak. So nevertheless, the important point is that at the center, the confinement of the electrons in the vortex core gives you this peak here. However, this you see only when the crystal is very neat. When the crystal is dirty, and you can make it dirty by, let's say, putting small amount of cobalt or small amount of tantalum, what you see is that this peak is washed out. And now what you have a feature which is completely flat. So this is like more like a regular normal. So here this is a very systematic study done in the 90s, where you put small amounts of tantalum, and you see that gradually this CDM peak becomes completely washed out. This is our data. All right. So this is what you should expect at the core of a vortex. What do we see? What we see is extremely unusual and very, very intriguing. What we see is this, that if I take this vortex lattice in our molybdenum germanium thin film, and I measure at this point A, I have a nice gap. This is away from the vortex center, that is fine. But even if I go at this point B, at the vortex center, even then here I see a soft gap. I see a depression. I have shown you what I should expect is either a peak or something that is flat. This is not just at one field. We do it for many fields. You see roughly the same thing, though of course the amplitude varies. The extent of depression varies. And we have done this for many samples, many vortices and so on. This is a feature that is always there. I can also track the zero bias conductance as a function of position along this line. And when I do that, you see that the zero bias conductance never reaches the normal state value of 1, but it remains less than 1, showing that there is some superconductivity that is sort of remaining even at the center of the vortex, which is very strange. Okay, so I can track this zero bias conductance here at the center of the vortex core and also far away from the vortex core. And this is how it varies at 450 millikelvin as a function of magnetic. There are two anomalies here, and I will come back to these anomalies later on, but there is overall an increasing trend. Okay, this has this kind of behavior been observed before? It has been observed only in two systems. One of them is high temperature superconductors. But in high temperature superconductor, the suggested mechanism is actually competing order. There is some order like charge density wave which competes with superconductivity, and that is the order that gives this. Now, this is completely irrelevant for our system, which is well studied for many, many decades and has no competing order. The second feature, that the second instance where such an observation was seen, is by us in our group earlier when we studied disordered niobium nitride. And here this is because in the presence of strong disorder, what was later shown by Amit Ghoshal and his collaborators, the vortices that you form are not Abrikosov vortices, but they are Josephson vortices. So this is our experimental observation, and here is a theory paper yet unpublished, but it's a very interesting physics. Nevertheless, it's not applicable here. Why is that? Because our systems are not disordered at all. To check that, we have actually made these maps of the coherence peak height and the zero bias conductance. And if you take a histogram of these quantities, you see that they are very sharply peaked. So we have a very homogeneous superconducting landscape. Unlike, for example, disordered NPN, where we see these Josephson vortices. There, if you do the same measurement, it will look like this. This is from our previous data. So therefore, these physics are not applicable here, and we have to think out of the box. So what we propose is the following. What we propose is that the vortex in this 2D system, which is very weakly pinned, is not static below the tip, but is actually fluctuating with a large amplitude. Sorry, at a large frequency. Amplitude, I don't know. But it's fluctuating below the tip. Now, if it is fluctuating below the tip, and if you measure the instantaneous conductance spectra, then that conductance spectra will also fluctuate like this. When the center of the vortex core comes below the tip, you will see something that is flat. When it goes away from below the tip, you will see the superconducting gap. However, you will never be able to do this measurement because STM is a slow measurement. It integrates over a much larger time scale. So if you do a measurement with STM, you will see an average of all these spectra, and which will be like this, even at the center of the core. So therefore, this is because actually now your vortex core and the vortex core becomes fuzzy because of this fluctuation. This fluctuation now it can arise. How can it arise? So it can arise from lattice vibrations. We know that the vortex lattice is like a solid, so we can have lattice vibration.
Pratap, you have about 10 minutes now.
Okay, thank you. I'll wait. So how do we verify this? So the way to, so before we verify, let us first try to have some predictions. So for this, we do some calculation. We take this vortex lattice, and this is a two-dimensional lattice, so it has the shear modulus and the compression modulus. The shear modulus is C66 and the compression modulus is C11. And we know that the shear modulus is much smaller than the compression modulus. This is in general true for most solids, and therefore the low energy mode will be the transverse vibrational mode of vortices. Now with this, now you can do an elastic theory of vortices. So you can assume a small displacement here, and then you calculate the energy. From that, you can effectively find a spring constant, and from the spring constant, you can now try to see how much amplitude of vibration you will have for 0-point fluctuation. What you will do is exactly what I have shown you in the first slide. Once you have calculated this omega, you will put H cross omega equal to the mass of the vortex, omega squared, into the amplitude of the fluctuation squared. And then you will put this expression back in and equate them. So it's a very easy derivation, and we are working here in the Einstein approximation. So we are not taking long wavelength. We are just we are not taking the short wavelength mode. We are only considering the long wavelength mode. All right. Now, if you do this calculation, then what you will get is delta A by A. A is my lattice constant and delta A is my amplitude of fluctuation. For quantum 0-point motion should go as h to the power 1/4. And of course, the prefactor will have the vortex mass in it. This is a very simple calculation, and of course, we are not theorists. But so when Surajit did this for a long time, we went on verifying. And later we found that Subir Sachdev and Bartosz had done a very complicated and sophisticated calculation using Green's function formalism in this paper. And the expression that we get from this back of the envelope calculation is almost exactly same with it, with just a prefactor of 0.6 that is different. All right. So this gave us a lot of confidence. And of course, we had a lot of discussion with Subir on this subsequently. You can also find out what it will be for thermal fluctuation, and that is very easy. For thermal fluctuation, is equate this to KT. And you will see that for thermal fluctuation, this delta A by A will be magnetic field independent. But how do I calculate delta A by A? For this, I have to simulate the conductance map in the presence of a shaking vortex lattice. So to start with, we simulate the conductance map by interpolating at the spectra at the center of the vortex core, which for a disordered superconductor will be flat, and far away from the vortex core, which is equivalent to the zero field spectra with the gap and coherence peak. And we interpolate between these two with a Gaussian weight factor, where the full width of half maxima of the Gaussian is twice the coherence. Now, then the interpolated conductance will look like this. This is a phenomenological theory. The reason we do this phenomenology is that right now there is no microscopic theory. There is something called Usadel theory that you can in principle solve, but it is computationally too expensive. Someone should try it. Okay, So with this, we can simulate the vortex lattice and at 10 kilohertz set. So right now I have no fluctuation inbuilt. And it will look like this. So if I have no fluctuation at the center of the vortex core, my zero bias conductance will be 1 because I have a normal core here. To check this, we again took this niobium diselenite crystal, which has a regular vortex lattice. And here there is no question of fluctuation. It is a three-dimensional vortex lattice. And you can see that we can simulate the spatial variation of conductance along this line extremely well. So this is the zero bias conductance. The line is the simulation. And this is the coherence peak height conductance. And the line is the variation. Here it is noisier, but again it captures the feature well. So with this sanity check, now we wanted to incorporate fluctuations. So fluctuations, the way we incorporate was within Born-Oppenheimer approximation. So we neglect retardation effect, which actually is justified here. And then what we do is we take these hypothetical instantaneous snapshots of the vortex lattice when they are fluctuating by displacing each of the vortex from its mean position by an amount delta R, which is bounded between 0 to delta A, and also in random directions. Each vortex is displaced in a random direction. We produce 200 such configuration and average them. When we average them, now you can see that the zero bias conductance variation along this line is like this, and it is now less than. So with this, now we can take our experimental data, fit it with this model, and extract the delta A by A experimented. And this is how it varies. Delta A by A as a function of magnetic field at 450 millikelvin, it varies like this. It gradually increases with magnetic field. So remember, the overall fluctuation amplitude is not increasing, but the relative fluctuation amplitude with respect to the lattice constant of the vortex lattice is what is increasing. And that is what should go as h to the power 1/4. This line is h to the power 1/4. And you can see that within the resolution that we have, the h to the power 1/4 variation captures the experimental variation of delta A by A very well. One more thing we can extract is the vortex mass. You know that the fluctuation amplitude depends on the vortex mass. And then from this vortex, if we plug in the formula and calculate the vortex mass from our model, we get 36 electron mass as the vortex mass. There is a very interesting estimate of the vortex mass, which is actually equivalent to the number of normal electrons inside the vortex core. And if you do this calculation, you get 32 electron mass. So we are very, very consistent. If you go to 2 Kelvin and do this measurement, now you cannot neglect the thermal part. The thermal part is magnetic field independent. And you can see at 2 Kelvin, the vibrational amplitude is marginally high. But we don't have that extensive data yet at 2 Kelvin. Okay, so I think I'm keeping the time and finishing. So this is to summarize. What I have shown you is the quantum zero-point motion of the vortex core in a vortex lattice, which actually is quite remarkable because it gives you another system other than helium, where you have a direct manifestation of the quantum zero-point motion, which shows essentially the essential quantum nature of the vortex core. Now, whether this vortex core, this zero-point fluctuation produces a quantum vortex liquid at t equal to 0, this is a more difficult question. We have not experimentally explored that in sufficient detail where I can give you an answer. So that is our ongoing problem. Thank you.
Very nice talk, Pratap. So clearly presented. I think the students would have benefited quite a lot. But Your clear presentation has put me into some fundamental doubt and philosophical question.
Okay, so there is a question already from Devjani Karmakar, I think. Let me answer this question. On the application of Marmin-Wigner theorem, yeah, so this is a question, this is a very important question. So Marmin-Wigner theorem tells you that, of course, in 2 dimension, you will never have a vortex solid. What means you will never have a true vortex solid. However, Marmin-Wigner theorem, of course, it's a theorem and it's rigorous, and it's true that you will not realize a true solid state for this 2-dimensional system. But for most experimentalists, Marmin-Wigner theorem is actually not very relevant. The reason is that Marmin-Wigner theorem tells you that you have no long-range order, but what you have instead is a quasi-long-range order that decays slowly as a power law. And power law decay is a very slow decay. So there have been estimates of how big a system you have to take before you see ramifications of this Marmin-Wigner theorem. And if you are working with a vortex lattice of the size of a football field, then you have to really consider Marmin-Wigner theorem. I consider samples which are sort of few millimeters by few millimeters, and over that length scale, I don't need to really consider Marmin-Wigner theorem. I have effectively a solid.
Okay, thank you. That explains actually whatever I have asked. Okay, thank you.
Yeah, anyway, we can also talk later. Is there
Any
any
other
other question? Yeah.
If there is no other question,
Yeah, one question. Can I ask?
yes, please.
Yeah, so what is so important about this emoji that you see the 0-point fluctuations? I mean, would you expect to see it in other amorphous superconductors as well?
So that's a very interesting point. I think that the 0-point fluctuation one should be able to see also in other superconducting films. You have to be possibly in the 2-dimensional limit. If you have a 3-dimensional vortex lattice, then I think the interactions are far too strong, and the 0-point fluctuation will be very small, too small to detect. So you need to do this experiment in thin films. Now, emoji is a particularly good candidate, as I said, because it's very, very weakly picked. So crystalline superconductors, for example, are not very good candidates for this, because crystalline superconductors have crystal defects, and those give rise to strong pins. But amorphous superconductors are good, and for example, the work that Gorakhnath presented yesterday, rhenium zirconium, that would be a very nice candidate to again look for 0-point fluctuation.
One more small thing is that this hexatic fluid is what is required also to, I mean, the hexatic state,
No. So for 0-point fluctuation per se, hexatic fluid is not required. But now what I'm saying is something that is just a hunch. I don't have a concrete proof of that. I think the reason we are realizing this hexatic fluid down to such a low temperature is probably because this 0-point fluctuation is present there. That is weakening the long-range order which you get in a solid.
Okay, thank you.
I think we should move on to the next speaker. Thank you, Pratap.
Thank you. Yeah, let me stop share.
Am I audible?
Yes.
Yes.
I am happy to welcome next speaker, Professor Shobana Narasimhan. He is another brilliant scientist, but of a slightly different variety. She is a theoretical computational scientist. Her area of research interest is computational nanosciences. She examines how lowering of dimensionality and reduction in size affects material properties. She got her PhD from Harvard and did her postdoc at Brookhaven National Laboratory in USA and Fritz Haber Institute of Max Planck at Berlin. She has been decorated with many awards and honors. The most important of them, Kalpana Chawla Women Scientist Award of Karnataka Government, election as Fellow of National Association of Science, National Academy of Sciences India, Allahabad, and election as Fellow of Indian Academy of Sciences, Bangalore, and election as International Member of American Academy of Arts and Sciences. Presently, she is a professor at the Premier Institute, Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. Today, she will give the keynote lecture on support doping to optimize the morphology, charge, and reactivity of deposited metal nanocatalyst. I was a bit curious whether it is deposited metal nanocatalyst or doped metal nanocatalyst. I hope to know it in the talk. Now I invite Professor Shobana to present our talk.
Thank
Shobana.
you. Thank
A
you.
small curiosity, personal curiosity. Were you in 810 Bhaskara TAFR colony?
Yes, I was.
Thank you. So my guess is not bad.
Yeah, so thank you for your kind introduction. And to answer your question, the nanocatalysts are both deposited on a support and doped, as I will explain. I would like to start by thanking the organizers for inviting me to give this talk. It is my great pleasure to give this talk. After that excellent pedagogical presentation in the previous talk, I hope I can be as clear. So I will be talking about tuning the morphology, charge, and activity of nanocatalysts by support doping. So I want to start on a slightly whimsical note by reminding you of this fairy tale that you might have heard or may not have heard. It's called the fairy tale of the princess and the pea, and I always thought it was a rather silly fairy tale. Those of you who have young children might have read it recently. It's that once upon a time there was a prince, and as princes do, he wanted to marry a princess. Okay, and the problem was to determine whether she was a real princess or not. And the test that his mother devised was that the candidate princesses had to sleep on a bed with lots and lots of mattresses, but under all these mattresses was a pea. And the idea was that if she was a real princess, she would be uncomfortable and she wouldn't be able to sleep properly. So to summarize the test that was designed for these candidate princesses, it was if there was a pea under all these mattresses, so you can see the pea right here, would she stay up all night in some upright, uncomfortable geometry, or would she lie down in a nice two-dimensional geometry and sleep the night through? So which geometry would a princess prefer? So I'm basically going to ask the same question in this talk. That's the most important question I'm going to ask. But instead of the princess, we're going to have a nanocatalyst. We're going to have a nanoparticle. Instead of the layers of mattresses, we're going to have layers of a support material. And instead of the P, we're going to put a dopant material. And the basic question we're going to ask is, when you do this doping, will the nanocatalyst have this sort of upright three-dimensional geometry, or will it have a flat two-dimensional geometry? And you can see, I will try to convince you that a lot depends on the answer. So I guess you can't see my titles, right? Because of this. So let me move this here. Okay. So supported nanoparticles as catalysts. Nanoparticles of precious metals on oxide supports are good catalysts for many reactions. For example, in cars, we have these catalytic converters that convert the noxious exhaust gases to less harmful products. So for example, in these catalytic converters, there'll be some oxide support, and then you have small nanoparticles of platinum, palladium, and rhodium. These are actually very expensive metals whose price fluctuates widely wildly with time, but most of the time they're far, far more expensive than gold. So what do these catalysts do? I'm sure you have all studied this in school or college. But basically, when you have a reaction, here you have your reactants, here you have your products, and you have to climb a reaction barrier to go from the reactants to the products. So you have to climb this energy mountain. And the main question to facilitate the reaction is whether you can reduce the height of the barrier. So that is what the catalyst does. It reduces the barrier from this dashed blue line to this red line. And so it makes the reaction much easier. And that is what we hope in finding a catalyst, that it will reduce the activation barrier. There are also other things that catalysts can do. It can be more selective towards certain products, etc. But this is the main thing that catalysts do, and this is what we're looking for. Does anyone know if there's some way I can get rid of this bar? Because it is spoiling my thing. Okay, I don't know what to do. Let me just see if I can.
It doesn't scroll down.
It doesn't
It
go
is just,
down lower than this. Okay, because it
we
is,
can see your slides perfectly. There's no obstruction.
there's no
Anyway.
obstruction.
No. All
Okay.
your the title is also clearly visible.
Okay, all right, then it's okay. Okay, so I'm going to talk for most of this lecture about gold, and gold has some very great surprises at the nano scale. So as we all know, gold is famously inert. So at the sort of macro scale, extended gold systems are famously inert. But it was discovered in 1987 that gold nanoparticles can be good catalysts. And since then, there's been an explosion of work on the catalytic properties of gold nanoparticles. And it is known that this catalyst activity depends very sensitively on the size. Like it can change significantly if you add or subtract just one atom from the gold nanoparticle. It depends also on the charge and the morphology of the nanoparticle, as well as on the nature of the support that the nanoparticle is deposited on. Also, depending on the reaction, you may want the nanoparticle to be positively charged, or you may want it to be negatively charged. So you would like to have control over all these properties. And in this talk, I'm mainly going to focus on how you can try to control the morphology and the charge, and you will see these two things are intimately connected. So the questions I'm going to ask are, can one tune the morphology of gold nanocatalysts on oxide supports? Can one tune the charge? I'm going to talk initially about aluminum doped magnesium oxide, but then I will talk about other dopants, and then I will discuss whether it really makes them into better catalysts. Then I will talk about whether this support doping also stabilizes the nanocatalysts, and then very briefly talk about other supports in other catalysts. So these are the technical details of my calculations, which I won't spend much time on, except to tell you that they're fairly standard density functional theory calculations. So the first question I have is whether one can tune the morphology of gold nanocatalysts on oxide supports. And the model systems that I will use are a single gold atom, a gold dimer, a gold trimer, and a 20 atom cluster of gold on magnesium oxide. Now, I call them model systems, but I want to say that these aren't just model systems in the sense that those of you who are following the field of nanocatalysis will know that one of the greatest hot areas these days is actually using these ultra small particles as catalysts. In fact, people work a lot now on single atom catalysts. So actually using just one atom as the catalyst. This is sort of interesting for two reasons. One is that these materials are very expensive. So if you can use just a single atom as your catalyst, obviously that's going to be much cheaper, but also very often you find that the reactivity, the catalytic activity is indeed much stronger when you go to these ultra small sizes. So we will start by using gold 20 as a model catalyst. This is a system that has been studied a lot for its catalytic activity. In particular, it's been studied for the oxidation of carbon monoxide to carbon dioxide. Now, it's known to have two stable isomers. There's this three-dimensional tetrahedral form and this planar two-dimensional form. But if you look at the energetic stability, this one is lower in energy, both in the gas phase and on pristine oxide supports. But there's reason to believe that this one might be the better catalyst. So the real question is, can you somehow tilt this seesaw? Can you flip the energetic balance so that it, instead of looking this way, it looks this way, so that this one becomes lower in energy? And we are not the first to have asked this question. Other people have also asked this question. So, for example, one suggestion that was made was that if you deposit an ultra thin layer of the oxide on a metal subboard, on a metal substrate, and then deposit the gold on that, then electrons from the metal tunnel through the oxide to the gold, and then it flattens out. Another suggestion that was made was that if you place the whole system in a rather high electric field of the order of 1 volt per nanometer, then also you see the same effect. You see that the nanoparticle flattens out. So now these are both very interesting suggestions, but they're a bit hard to implement in practice. So we were looking for something that would be easier to translate to realistic applications. So the suggestion we made back many years ago was that you dope the oxide support. So for example, if you have magnesium oxide as your support, then you replace some of the divalent magnesium atoms with trivalent oxygen atoms. So this is paleovalent doping. And the hope was that then you would see this transition from a three-dimensional morphology to a two-dimensional morphology. So does this suggestion work? So at small doping, so what I plotted here is the difference in energy between the planar and the tetrahedral isomers versus the dopant concentration. So at small dopant concentrations, the three-dimensional morphology is still favored, but at sort of after about 0.4% doping concentration, you find that the planar morphology is indeed favored. And so this idea looks like it would work. So this was a theoretical prediction that we made. And our great happiness, within a very short time, this prediction was confirmed. So there were experiments done in the group of Freund at the Fritz Haber Institute in Berlin. And so they used our idea, but they used it on a slightly different system. So instead of using magnesium oxide as the support, they used calcium oxide. And instead of doping with aluminium, they doped with molybdenum. But otherwise, the whole idea is the same thing. And so these are STM images of their system. So when they dope the gold nanoparticles on the pristine oxide, you can see that the nanoparticles have these three-dimensional shape. But when they place the gold nanoparticles on the doped oxide, they have these flat sort of chapati-like shape. And if you measure the height of these nanoparticles, they're only 1 atom thick. I should also mention that these nanoparticles are much larger than our nanoparticles than the 20 atom nanoparticle on which we did our original calculation. So they're of sort of tens to hundreds of nanometers in size. So it seems to work also for much larger sizes. So this is, I can tell you that as the theorist, this is one of the most exciting things that can happen to you, which is you make a theoretical prediction and then someone does an experiment and proves your prediction right. So we were happy to know that it happens, it works at large sizes, but because of the great interest in ultra small sizes, we wanted to see what happens at ultra small sizes. So we then went to do the calculations for these ultra small sizes of nanoparticles. So if you look at a single gold atom on the pristine surface, it is absorbed, ate up an oxygen atom. But if you put it on the doped support, so this is again magnesium oxide with the purple aluminum dopant, it changes its absorption site and it goes to the hollow site instead. Of course, for a single atom, there's no question of transitioning from a 3D morphology to a 2D morphology or whatever. If you look at the gold dimer on the pristine oxide, it is sitting upright. And then on the doped oxide, it lies flat. So basically, you go to wetting morphologies when you dope with an electron donor. And if you look at the gold primer, it again lies flat when you dope with an electron donor. So you have this tendency that you start wetting the surface when you dope with an electron donor. So why does this happen and what happens to the charge density? Is there charge transfer between the support and these deposited gold nanoparticles? So that's the next thing we will look at. So this is a single gold atom deposited on pristine MgO, that is undoped MgO. So even on the pristine MgO, there is some charge transfer between the MgO support and the gold atom. So these lobes show the charge transfer that occurs. So a magenta color indicates that electrons are gained and blue color indicates that electrons are lost. So you see that electrons are lost by the support and gained by the atom, as a result of which the atom gains a charge and becomes negatively charged, minus 0.26 electrons. However, when you dope the support, then this charge transfer is much greater, and that's because there are these extra electrons from the aluminum floating around, and the charge, you can see that this magenta lobe is bigger, and now it has a charge of minus 0.83 electrons as opposed to minus 0.26 electrons. So you can look at it for different sizes. So if I go to the dimer, to the trimer, to the 20 atom cluster, on the undoped support, the charge increases. It goes from minus 0.26 to minus 0.28 to minus 0.5 to minus 0.94. And on a support that has been doped with aluminum at a 2.78% concentration, again, you see in every case, the charge becomes much more negative on the doped support. It has minus 0.83, minus 0.87, minus 0.95. And on the 20 atom cluster, you have a quite significant negative charge of almost minus 4 electrons. So this is very interesting from the point of view of applications in catalysis, because it is known that negatively charged clusters can be very good catalysts for oxidation reactions, for example. What about other dopants? We used a cationic dopant and an electron donor. Can you use anionic dopants? Can you use electron acceptors instead of electron donors? Can you use, what happens if you use transition metals with variable oxidation states? So let's look at a section of the periodic table. So this is our support. There's magnesium here and oxygen here. So what we had considered so far was that you go one element to the right with respect to magnesium, and that would be your cationic donor. The other options you can have is that you go one atom to the left and you would have a cation acceptor, or if sodium doesn't work, which we find, I will show you in a moment, doesn't work so well, you could also consider lithium and potassium. And similarly, for the anion, if you want a donor, you go from oxygen to fluorine. And if you want an acceptor, you could think of going to nitrogen, or if that doesn't work, you could go to phosphorus. So I will show you a combination of our results here. And how do we measure how good a dopant is? So now, the naive expectation from this periodic table is that if you go to a donor, you would expect that it would surrender one electron to the system. It would donate one electron to the system. Whereas if you have an acceptor, you would expect it to accept one electron from the system. But this isn't quite what happens. So the actual doping efficacy is sometimes less. So how you measure this efficacy is you look at the actual charge. It's called QT because it's called a topological charge. But I should warn you that this topological charge has nothing to do with topological insulators or Berry phase or anything like that. It's called topological charge because it is determined by looking at the topological properties of the charge density, divided by the nominal oxidation state that you expect if it actually donated one electron or accepted one electron. And you can see here that it isn't always one. It is one if you take this ratio for aluminium, lithium, or fluorine, but it goes down as low as 0.6. Now, to find some trends in this, you might think that this should depend upon the difference in electronegativity between the dopant atom and whatever you have in the oxide support. For example, if your dopant is a cation, you might think that it should depend on the difference in electronegativity between your cation dopant and the anion you have, which is oxygen in the support. But that doesn't give us trends at all. We have some totally random results. And we found that the descriptor, as it is called, is if you look at the difference in the electronegativity divided by the difference in the atomic size, okay, then this delta chi by delta R, if you plot it, then you get this kind of sigmoidal kind of plot. And actually, we first got this plot for a few elements and then used this plot to predict. For example, we were having a lot of trouble finding a good acceptor. We found a good donor, which is aluminium, which works very well. But we had a lot of trouble finding a good acceptor and used this kind of plot to predict that lithium would be a better acceptor than, for example, sodium or potassium, etc. So let's try all these other dopants, and you find here the different, I've shown results here for a single atom on the doped supports, where you have fluorine, aluminium, nitrogen, sodium, lithium, all at 2.78% doping concentration. The different colors here show, the yellow arrows show you where the dopant atom is, okay? And red lobes again show you, like before, that you have electron gain, and blue lobes show you have electron loss. So as in these two cases, you have what you expect, which is that the gold atom becomes negatively charged. In these two cases, it's interesting because the gold atom becomes positively charged. And as I told you right at the beginning, for certain reactions, you want the atom to become positively charged. It is expected to be a better catalyst if it is positively charged. And this is actually a rather challenging thing, making gold positively charged, because gold is highly electronegative. So it is interesting to find dopants that can make gold positively charged. This is similar results, but for the 20 atom cluster. And you can see that by varying the dopant, you can vary the charge on this 20 atom cluster from minus 3.96 electrons to plus 0.49 electrons. And once again, you see that it's much easier to make it negatively charged than to make it positively charged. And that is, of course, because gold is highly electronegative. So you can tune the charge by varying the dopant. And I told you that we found a descriptor that allows you to predict which descriptor will work in making it negatively or positively charged. But you can also vary the dopant concentration. So to predict the morphology, now these calculations are all a bit expensive to do. So is there something that will some other descriptor which includes not just the dopant that you have, but the dopant concentration, and will allow you to predict both the change in morphology and the change in charge? And we find that one very good such descriptor is the work function of the doped support. That is the work function of the oxide with the dopant, but without the gold deposited on it. And this calculation is a very quick calculation to do. Whereas once you put the cluster on it, once you put the gold nanoparticle on the support, that is a much harder calculation to do and much more expensive calculation to do. So we find that, for example, these three graphs show the difference in energy between the two competing isomers. For the gold monomer, this is the difference between adsorption, A-top oxygen, and on the hollow side. This is for the dimer, it's between the upright and the flat geometry. For the gold 20, it's the difference between the tetrahedral and planar isomer versus the work function. So you can see that you get a nice linear behavior in all three cases. So this means that you can predict, like if you can just calculate the work function of your doped support, then you can predict which geometry it will have. And similarly, it can also predict the charge that you have. So in these cases, it is the charge on the single gold atom, the dimer, and gold 20 versus the work function. So you can use the work function as a quick calculation that will predict both the morphology and the charge that your system will have. What I talked about so far was gold on aluminum doped MgO. But then if you remember, I told you that the experiments in the Freund group were done on molybdenum doped calcium oxide. And so we also did calculations on the molybdenum doped calcium oxide. And indeed, as one might expect, when you do that, you see once again a transition from a three-dimensional shape to a flat planar shape. But what is quite interesting is to look at the charge transfer plots. This one is for aluminum and this one is for molybdenum. Now, if you look carefully, what happens is that the aluminum, as soon as you dope the support, it gives away its electrons to the system, okay? And then those electrons are delocalized, and then when you look at the charge transfer, you see that the gold is negatively charged, but you don't see any blue lobes localized anywhere in the support. That is because the electrons were delocalized, and from the whole region, the electrons went. However, for the molybdenum, you see blue lobes in the vicinity of where the molybdenum dopant was. That is because molybdenum doesn't change its charge state when you put it in the dopant. It only in the oxide, it only changes it when you deposit gold. Now, this is very interesting and important for applications because in real systems, you have a lot of defects and dislocations, etc., which might trap this negative charge so that it cannot go to the gold. So if you have a dopant like molybdenum, which only surrenders its electrons to the gold, that is very important and very interesting for applications. So now I come to my next question, which is, of course, what has motivated a lot of the work, which is whether support doping can make the gold nanoparticles better catalysts. And for that, we're going to study a very simple, one of the simplest possible model reactions, which is we're going to look at the dissociation of oxygen, because this is an important reaction that takes place when you have oxidation reactions. So we take the particle on the doped and undoped supports. We put this blue molecule, which is the oxygen molecule, and we look at the barrier for dissociating this oxygen and see what happens. And as you remember, I told you at the beginning, if it's a good catalyst, it will lower the barrier. So we looked at the barrier for dissociation of oxygen. So first, let's look at the adsorption of oxygen. Now, the top panel, the numbers in magenta show you the adsorption energy of oxygen. So a negative number means that adsorption is favored. A positive number means that it doesn't adsorb. So let us look, for example, at gold 20. You see that on the tetrahedral gold cluster on the undoped support, oxygen doesn't even bind. Okay, so it's not going to be a good catalyst at all. But when you dope the support, then you have binding and the adsorption energy is minus 0.69 eV. So this already tells you that maybe it's going to be a better catalyst. And when you calculate the dissociation barrier, so this is how we do it in a calculation. So we adsorb the oxygen and then we stretch the oxygen-oxygen bond until it breaks. And what is plotted here is the energy of the system versus the oxygen-oxygen distance. And you can see that as the bond is stretched, the energy first goes up and then goes down, and so till it dissociates. So this distance from here to here is our dissociation barrier, and that is what we compute on the doped support and the undoped support, and we compare them. And we find that indeed on the undoped support, the dissociation barrier is 0.68 electron volts, whereas on the doped support, the dissociation barrier has reduced significantly. It has come down to 0.29 electron volts. Okay, so it has more than halved. And if prefactors stayed the same, this would imply that the reaction rate increased by more than 5 orders of magnitude at room temperature, which is obviously a very good thing if you want a catalyst. So here are some comparisons of what is happening for various things which give you some idea of how the catalyst works. So this is the charge on the gold. These are the reactions for 1 atom, 2 atom, 3 atoms, and 20 atoms. The sort of pink triangles are what you have for the 3-dimensional isomer or the upright isomer, and the black rhombi are what you would have for the flat planar wetting isomer. And you see that the charge, it becomes more negative when you have the wetting isomer on the doped support. and this, sorry, I should explain again that the upright isomers are on the undoped support and the planar isomers are on the doped support. So you get more charge when you go to the doped support. And then when you absorb oxygen, this charge is transferred to the oxygen. So you get more charge transferred to the oxygen when you dope the support. As a result of this, the oxygen-oxygen bond length increases on the doped supports. And of course, when you increase the oxygen-oxygen bond length, that means that that bond is easier to break. And indeed, when you calculate the dissociation barriers, you see that the dissociation barriers are lower on the doped support than they were on the undoped support. So here, this is looking at things versus concentration. So this is for the 20 atom gold cluster and looking at the barrier for dissociation at two different adsorption sites. This is called P1, this is called P2. And you see that as you increase the dopant concentration, the dissociation barrier falls more and more. Now to try to understand why this happens, there are some models which are very popular in the catalysis literature. So in these models, people look at the density of states of the catalyst, okay? And so this is the density of states. So you have, if you have a transition metal or a noble metal, you have S and P electrons, which have a broad and low density of states, and you have D electrons, which have a much sharper and peaked and narrower density of states, okay? And for transition metals, the D band is partially filled. For noble metals, the D band is almost fully occupied. And what's very popular in studying catalysis by transition metals and noble metals is to say that the key parameter is the D band density of states, and that you look at the center of the D band density of states, and that as it goes higher and higher up with respect to the Fermi level, you get a better and better catalyst. So that was the first thing we looked at to try and understand if that can explain this better catalytic activity. So for example, for gold 20, as a function of doping concentration, this is the D band density of center of the D band versus doping concentration. And we find the opposite trend, okay? We find that the D band center goes down and not up. So this is a counterintuitive result in the sense that if the D band model explained our results, the opposite should be happening. So to try and understand what's happening, we look at where these extra electrons are going. And so this is the D band filling versus doping concentration. You see almost no change in it. And if you look at where these extra electrons are going, they're mostly going into the S and P bands. Now, in the D band model, it's assumed that the S and P bands are static. Nothing much happens there. But this approximation is clearly wrong. So in our case, because of
interruption, we are about 8 minutes or so.
Yeah, we'll finish.
Thank you.
Okay. So because the S and P bands are low and narrow, even if you have a small change in their filling, they move a lot in energy. Whereas the D band center, because of the shape of the D band, does not move much. Okay, so there is this model due to Norskov and Hammer, which talks about what happens when you have an adsorbate coming on a metal catalyst. So these are the molecules bonding and anti-bonding state. They are renormalized due to interaction with the S and P orbitals of the metal. Then with interaction with the D band, they split into, again, anti-bonding and bonding states. And this is where the Fermi level of the metal is placed. And based on that, they derived such a formula for the energy of the transition state. Okay, now this is the matrix element of the interaction. This is the energy of the anti-bonding state of the molecule after renormalization with the S band, and this is the D band center. And in this whole discussion with the D band center, there was this assumption that you make this term small by tuning ED. And what we're going to say now is, no, you not only do that, you can also push down EA prime by tuning what happens to the S and P bands, which is what we think is happening mainly in gold catalysts. So the new descriptor we have is not just ED, but ESP minus ED, okay? So this is a difference in the band centers of the SP and the D. And when you do that, you see that you have this kind of linear behavior, which correlates excellently with the dissociation barrier. So this, we believe, should be the new descriptor for the reactivity of gold catalysts. So to check this, see, one of the big puzzles in the field is, why is gold a good catalyst at nano sizes? And so to do that, we can take extended gold systems and artificially reduce their coordination by going from FCC gold to BCC gold to simple cubic gold to diamond, etc., and to other low dimensional systems. Or we can look at gold nanoparticles, as we have done. And if for these systems, if you look at what happens to the D band center, as you reduce coordination, you indeed find that the D band center moves up in energy. And this has been the traditional explanation for why gold is a good nanocatalyst. But we find that in addition to that, there's an even stronger effect, which is that ESP minus ED goes down. And we believe this also contributes to the catalytic activity of gold nanocatalysts. Okay, so this ESP minus ED, we believe as coordination number decreases, this is an important reason for the catalytic activity of gold nanocatalysts. So one of the last things I want to talk to you about is, okay, so this movie is not working now. Okay, this was supposed to be a movie that showed you gold nanoparticles sintering. So one of the important reasons why, okay, maybe if I remove my pointer, let's see if it works. Okay, yes. So this is a movie which shows you that realistically gold nanoparticles diffuse on the surface. And you see that here two gold nanoparticles fuse together. And now these two will move and they will also fuse together. So this is called sintering. And this is one of the main reasons for the degradation of nanocatalysts. So we wanted to know whether we can also explain what would happen about sintering, whether this support doping has any effect on sintering. So we look at the energy change on sintering. So this is two gold monomers coming to make a gold dimer. This is the diffusion barrier that they have to, for one monomer to diffuse and join another. And this forms gold dimer. On aluminum doped NGO, we find that first of all, the diffusion barrier is lower. However, this is now goes up in energy rather than down in energy. And so this process is unfavorable on the dope support. Okay, so you would think that sintering becomes much more unlikely, which is a very good result. So you wouldn't have sintering be favorable. Similarly, you can look at 3 gold atoms coming to form a trimer. And here, though it remains favorable, it is not as favorable as it is on the undoped support. And so once again, it is much better to have a doped support. The last question, just one slide. What about other supports and other catalysts? What about two-dimensional material supports, organometallic catalysts? We've done some work on nitrogen-doped graphene. So again, the same idea that if you dope nitrogen in graphene, it's an electron donor. And we've looked at cobalt phthalocyanine, which is known to be a catalyst. And the interesting thing here is that if the cobalt phthalocyanine molecule sits atop, these were done in collaboration with a STM group in France. So if it sits atop a single nitrogen dopant, it doesn't change its oxidation state. But if it sits atop 2 nitrogen atoms, then there's a significant charge transfer, which is enough to change the oxidation state of cobalt. And there is reason to believe that it will then become a much better catalyst, and work is ongoing on that. So I'm done. So just to summarize, LU-valent doping of the oxide support can tune the charge of supported gold nanoparticles. A suitable choice of dopant and dopant concentration can make the gold nanoparticles negatively or positively charged. We've developed descriptors for the choice of dopant and dopant concentration. This doping and change in morphology affects the reactivity of the gold nanoparticles. We've also developed a descriptor, ESP-ED, for the reactivity of the gold nanocatalyst. And we've also shown you that this hinders the sintering of supported nanoparticles. These are the papers that we have published on the work I have presented in this talk. These are the people whom I work with. Most of them are my former students or current students. No, actually, they're all former students. This is Aruna, who was a summer student who worked on some of this. This is Stefano De Gironcoli, who's at CSA in Trieste, with whom I did some of the early work in this project. These are the people from whom I got funds and computational resources, and thank you very much.
Very nice, Shobana. You really timed your talk very precisely. I admire you. Any
Thank
question?
you.
Hi, I have a question. I am Dejani Karmakar from BIRC. May I ask my question?
Yes, of course.
Yeah, actually, if you look at this few number of gold atoms, experimentally that cannot be sustained without passivation. Now,
Without what?
Result be
Sorry,
without
Dejani. Without what?
Without passivation. Passivation with some kind of organic, material.
Okay, so
will this result remain same? Will this result remain same with passivation also? Because few number of gold atom cannot be sustained.
Okay, so people are working on how to stabilize these very small clusters. But of course, people are also working on passivated gold clusters with the organic ligands. So initially, the belief was that the passivation destroyed the reactivity. But recently, there's been a lot of interesting work that shows that there can be certain ligands which actually even boost the reactivity. So, for example, my former student Nisha Maman, who did actually most of the work that I presented. She is now working as a postdoc in a group of Hakkinen in Finland. And this is exactly what they're working on. They're showing how putting in ligands actually boosts the reactivity.
Okay, but another thing is that usually gold is having this 5D and 6 is itinerant delocalized electron, because they are chosen as a very natural contact for any semiconductor or anything. So they usually donate this electron and become positive very easily. But for your case, I have seen that your golds are maybe that 20 atom from whatever cluster you were showing. Is it forming a kind of quantum dot, and that it is having a kind of band gap, which is leading to your D-band center movement and other things? Because there is
actually in all the cases we have considered, it isn't something special about the 20 atom. We are finding that the gold wants to become negatively charged unless you force it to become positively charged by putting it over an electron acceptor.
Yeah, usually that the few atom gold, not only 20, but few atom gold. There is a in 2014, there was a work by Shiva Vandari and others, SES Nano, which shows that few atom gold is actually a semiconducting system. So it actually opens a band gap. And then has it anything to do with this your D-band center movement? So that it is becoming actually a semiconductor, and that's why your D-band center is moving.
I have to look at the band structure and check, but that was not my impression, but I will check again.
Okay, thank you so much. It's a very nice talk.
Thank you.
Any other question? Short question?
There's a question from Shobik here.
Hello, hi. Am I audible?
Yes.
Yeah.
Yeah, I have a quick, actually, two related questions. So first, about this tetrahedral to planar transition in morphology that you showed in very earlier part of your talk.
Yeah.
Yeah, so I was wondering that if you can explain the mechanism, in the sense, is it just the changing the surface energy of the aluminum doped MgO that is doing the trick? And the related question was that if you can comment on the role of temperature, in the sense, like we can always give sufficient kinetic energy, and many a times the oxygen sublattice of MgO, because of the relevant element oxygen bonds, can stabilize such as planar structure, if you think about the epitaxial stabilization from that point of view. So I was wondering if you can comment on the role of temperature in trying to stabilize these sort of different morphologies on MgO without even going into the dope.
Sorry, what was your first question? It was about what?
About the aluminium doped MgO, like what is exactly happening, in the sense, is it just a
Okay, so I tend to think that is mostly an electrostatic mechanism, that if you when you put it on the electron on a support dope with an electron donor, then there is a donation of charge and the cluster becomes negatively charged, and then the way for it to reduce its electrostatic energy is to flatten out. Okay, but I realize that this cannot be the whole answer, because then that should be a symmetric argument, in the sense that it should also happen when it becomes positively charged.
Right.
But it doesn't happen there. So it's not completely electrostatics, I guess, but that is what I tend to think of it as. And temperature wise, no, because our calculations are done at 0 temperature, so they don't have temperature effects. But the experiments are done at room temperature. And and experimentally, they see that they tend to clump up and be 3-dimensional unless you do something to flatten them, like, dope or something. I guess you're asking what if we go to very high temperatures or something like that, right?
Yeah.
I don't know if anyone's looked at that. I don't know the answer. For that, you would have to look at the vibrational energy of the two systems and compare them. And I don't think anyone has looked at that, so I don't know the answer.
I mean, I just make comment maybe in the sense that, for example, when people are doing aluminum on semiconductors, it's all about raising the diffusion barrier. So we have to grow at very low temperature from them to sticking together, and then you get a planar structure. I was wondering if someone has tried to grow it at lower temperature, you know, like not giving enough kinetic energy for them to clump together, and that will make a surface.
So you're saying low temperature might cause wetting?
Yeah, yes.
I think that has been tried and didn't work.
Okay. Thank you. Yeah, that's a great thought.
Running short of time. The organizer would like to maintain the time. Thanks, Shobana. Again, I learned something new, very new, I would say. You inverted the concept for me. Thank you very much. Both the speakers gave engaging talks. If it were a physical meeting, we would have had a loud applause, which we miss now. I think there are some clapping symbols available. The organizer should arrange for it next time.
Okay,
thank you. Take over, please.
Yeah. So thank you very much, Professor Nagarajan, for kindly chairing the session. And I would really like to thank both the speakers. We'll meet again in 10 minutes for the next session at 11 o'clock. Thank you. Hello, Professor Nigam, are you there? Atikur, are you there? Hello, is Atikur there?
Yeah.
Yeah, could you just,
This is Atikur.
yeah, can you just share your slides? We'll just check it once.
Yeah, sure.
Go to full screen.
Is it fine?
Yeah, just scroll through once. Yeah, so fine. It's
Yeah.
working. Yeah, thank you. Prasanna is also there, I think.
Yeah.
Yeah, could you share your slides? Atikur, could you just unshare? We'll just check the slides for the next speaker.
Hello. Can you see my screen?
Yeah. So can you scroll through? Yeah, perfect. So you can unshare. Professor Nigam, are you there? I see him.
I'm here.
Yeah. Thank you. Sir.
Can you see me?
I can't see your video is not on.
One
Your audio
minute.
is working.
Okay, 1 minute. Yeah,
Yeah,
now it's
now
okay. Okay.
it's working.
Yeah.
Okay. So we'll just start in 3 minutes.
Okay.
Okay.
Hello, Nigam. How are you?
Hello, Professor Narayan. Thank you. How are you?
Fine.
Hearing your voice after a very, very long time.
Yes, you will hear a little more because I have something to ask you.
Sure.
But that is after the conference.
Sure.
Are you in India or outside?
I'm very much in India. My son has moved back to Bombay.
I see. Remaining after the conference.
Okay. Yeah.
Okay, so it's 11 o'clock. So we are ready to start the next session, session 2 of day 2. So I would like to request Professor Nigam to chair this session. So Professor Nigam, superannuated from TIFR. He's also the co-chairman of MRSI Mumbai chapter. He has made notable contribution in working with correlated materials, mainly magnetic materials. So over to you, sir.
thank you, Dr. Sangeeta, for inviting me to this chair this session. And without taking further time, I think we will start the session. And welcome to all the online participants and audience of this to this session. So we have 2 invited talks. Rest are contributed talks. I think 3 of them. So the first talk is by Dr. Atikur Rahman from ISER Pune, and he is going to talk on fabrication and optoelectronic properties of mixed dimensional van der Waal heterostructures. So I request Dr. Rahman to start to give his talk. Thank you.
Thank you, Professor Nigam, for the introduction. Am I audible?
To me,
Yeah,
yes.
yeah, you're right.
Okay, great. So first, I would like to thank the organizer for inviting me. Today, I'll be telling you about the fabrication and optoelectronic properties of mixed dimensional van der Waal heterostructures. So this is the lab members who's working on various projects. But today, I'll be talking mostly about Gokul and Brinda's work here. So I'll divide my talk into 2 parts. First, I will tell you about the growth of large area monolayer of transition metal dichalcogenides. And I'll tell you about this growth promoter, this sodium silicate, which works pretty well for growing this kind of monolayers. And then I will tell you about how we are fabricating this mixed dimensional van der Waal heterostructure, which is basically a silicon MS2 heterostructures, 2D, 3D heterostructures. And how by tuning the dielectric environment, we can enhance their photoresponse. I'll tell you about that as well. So those who are working with growing this material, most of us using NaCl as a growth promoter in chemical vapor deposition, and NaCl works pretty well. But while working on a different project, we came across this chemical sodium silicate. And by looking at its mechanism in anodic bonding, we realized that it can be a very good growth promoter for this transition metal dichalcogenides. And then we tried with this growth promoter, and we found that yes, it's working pretty well. And we grew so far MOS2, WS2, and WSC2. And we are pretty confident that whatever TMDs you can grow using NaCl, it can probably grow it much better with sodium silicate. And you see there Raman and PL spectra, the FWHM of PL of these monolayers are pretty narrow. So this also tells that the properties of these, the quality of these samples are pretty good. As you know that in case of CVT growth, this growth parameters has a very narrow window. And if you change these parameters a little bit, then it's very difficult to reproduce the result or get a very good quality samples. Good quality monolayers. Sometimes the size might be small. And there are a lot of other things that might ruin your ultimate result. However, what we found that if you're using this growth promoter, this sodium silicate, then this window is pretty large, this parameter window. Like here, I showed that if you change the concentration of the growth promoter by 2 orders of magnitude, you're still getting almost the same result. And also the temperature window is now pretty large. Like for MS2, you can grow samples at as low as 500 degrees Celsius. And the flow rate can be, you can change 3 times the flow rate and still you will get nice monolayer without much problem. And another thing is that now with this growth promoter, it's so strong that you don't need that much of precursor. Very less amount of precursor can grow this 2-dimensional TMDs. Actually, one point what happened is that we didn't put the precursor, and whatever was coated on the tube, we still were able to grow a really large area, nice monolayer of TMDs. So it is indeed a very strong growth promoter. And to show that it's better than or it's stronger than NaCl, what we did, we took several substrates and alternately coated them with NaCl and water glass and kept it inside the CVT. And what we found that on a particular conditions, we are getting only monolayers on the water glass, but not on the water glass coated substrate, but not on the NaCl coated one. So it is indeed much stronger than NaCl. Now, how it forms this MOS2, the actually reaction mechanism is same as NaCl. It forms the same intermediate compound, which is Na2O7, and we did XRD and EDAX to confirm that. We also did XPS to confirm this component. And in the next reaction, what happens is that when it reacts with sulfur, then you get MOS2. And this is basically the intermediate compound, and it's XPS. And after reacting with sulfur, you get this MOS2 layer. So it is confirmed that the intermediate is same in both the cases. Now to check that how strong or how good this growth promoter is, what we did, we tried to do conformal growth of this TMD monolayer. So we took a piece of silicon and then etched it to make a trench. And just to make it optically visible, I mean, make these monolayers optically visible, we grow 300 nanometer SiO2 on top of it. And then we try to grow this MOS2 on these substrates. And here you can see that now even the trench is there, but as the 300 nanometer SiO2 present, this MOS2 layer is easily visible. And this is the corresponding ACM image. It's taken at an angle so that it looks a little bit elongated. And a high resolution image clearly shows that, yes, it is indeed forming conformally. But still the radius of curvature is not that much here. So what we did, we tried to push the limit a little bit more. And we made some trenches where you have a really sharp notch. Here, actually, you have a notch of nearly 20 nanometer radius of curvature. And we use this substrate. We actually made this substrate by two-step wet etching technique. And then we use it to grow the MOS2 monolayer using this water glass as a growth promoter. After the growth, when you try to image it, so we cleave it, and you can see that the monolayer got ripped here, so you can easily see the contrast. So if you see the high resolution image, you can see that monolayer is growing nicely conformally along this high, curvature trench. So this actually is very useful for many applications, and we actually have a future project where we need this kind of monolayer grown on a nanotextured substrate. In this image also, you can see this part, the monolayer got ripped here, so that probably you can see the monolayer. So that all these results shows that, okay, this monolayer forms conformally along any kind of nanotextured substrate, which is kind of unique. With NSL, it's not that easy to grow. Now, you know that if MOS2 is kept on a curved surface, then due to the strain, the band gap reduces, and as a result, you see enhancement of PL at the curvature region. This is known as a funnel effect. To check that whether we can see this kind of funnel effect on our samples grown on nanotextured surface, we collaborated with Dr. G.B. Pavankumar at IISER Pune, and we did PL mapping on that. And we found that, yes, indeed, the PL is enhancing at this curvature region. You can see a cross section here of this PL mapping. This also tells us that the samples are pretty good quality. We can grow continuous monolayer over a large area substrate, and they are not only optically continuous. We made a connection to 1 centimeter apart, and you can see that by illuminating LED, it is showing photoresponse. So the samples are also electrically continuous throughout this 1 centimeter region. We actually grow even more than that, large samples. So just to conclude this part, that this growth promoter is pretty good. We also did the electrical measurement of this, and with salt, we generally found 1 centimeter square per volt second mobility, or even less than that. But with this growth promoter, the maximum mobility that we achieve is 7.4 centimeters square. And we regularly get mobility between 4 to 5 centimeters per volt second. So that tells us that the mobility is also high compared to the salt grown samples. Okay, now we use this monolayer. We have this nice monolayer. Now we make the heterostructure of silicon MOS2. Why we want to do that? We want to test what is the effect of dielectric environment on two-dimensional material. As you know that because it's ultra-thin nature, so the electric fields are not screened in the perpendicular direction, means out of plane directions. As a result, the photogenerated carriers, they're strongly bound, so that the excitonic binding energy is pretty large. But if you put them in a high dielectric medium, then what happens is that because of the screening of Coulombic interactions, the binding energy reduces. So now the excitonic binding is pretty low. And how that helps? Now, if you apply a small electric field, you can easily separate this photogenerated carrier. and as a result, you can get a high photocurrent. So to test this thing, we made this silicon and MOS2 heterostructure. We took silicon as a three-dimensional, because this three-dimensional material, whatever the change that we'll be seeing is mostly due to this 2D. So that's why we, instead of using a van der Waals heterostructure of two-dimensional material, we use one as a three-dimensional material and one 2D material. We also use the silicon, this is a P-type silicon, so it can easily make a nice PN junctions. You know that in van der Waals heterostructure, as the charge transfer takes place between the layers through tunneling, so they are generally pretty, efficiency is pretty low. So we thought that can we improve this efficiency by tuning the environment dielectric and whether we can enhance the photoresponse. So first we need to make this device. So we took a degenerately doped P-type silicon with 300 nanometer SiO2 coating, and then etch a part of it almost 250 nanometer by reactive ion etching. Actually, this gives us a very vertical profile so that the contact area, it's easy to find the contact area between MOS2 and silicon. The rest 50 nanometer SiO2 we removed by BOE etching, so it's a weight etching technique. The reason is that we don't want any defects to generate due to this high energy ions. So the last 50 nanometer we removed by BOE. And finally, we did another step of very dilute HF etching for a very short time. This actually helps to passivate the silicon surface. This actually makes this hydrogen terminated silicon surface, and that is very important for making MOS to silicon heterostructure. The reason is that if there is a charge transfer takes place, then it won't be a van der Waals junction. So we want to make sure that this MOS2 and silicon makes a nice van der Waals junction. We transfer this MOS2 by polystyrene coating based transfer technique. So once, I mean, before transferring, we definitely checked the quality of the MOS2. And here you can see that the WHM is pretty less. It's only 57 millielectron volt, which is kind of almost same as the exfoliated sample. So the quality is pretty good. So this is the, I mean, after transfer, you can, this is the ACMN optical image. Here you cannot see the MOS2 because now there is no contrasting SiO2 layer. It's only the silicon, whereas you can see it easily in the ACM image. This P-type silicon and MOS2, they form actually type 2 hetero junction. What does it mean? It means that the conduction band minima and the valence band maxima, they are now residing in two different materials. So once you transfer this, then we fabricate the device. We put two electrodes on the MOS2 also so that we can independently characterize the MOS2, and the connections on the silicon is somewhere outside this image. So once we have it, then we study their IV characteristics. Here you can see that in presence of, in absence of light, in dark IV characteristics, it's showing rectifying diodic behavior, which is expected for a good PN junction. And in presence of light, you do see in the reverse bias, you see a significant amount of photocurrent, and the photocurrent is also saturating at a slightly higher bias, near around 3. Now we also just studied of this current, and we found that carriers contributing. But the photogenerator, in presence of light, the current is actually decreasing with increasing temperature. So it tells us that we are generating sufficient amount of carriers by light, so that the thermally generated carrier is not really contributing to the total collision increases. As a result, the current reduces slightly. But this, this asymmetric IV characteristics can also come due to the Schottky barrier formation. And to make sure that the asymmetry is not due to the MOS2 and gold Schottky barrier formation, we studied this junction. And what we found that it gives a very linear IV characteristics. So that tells us that the MOS2 and gold junction is ohmic. So definitely whatever the asymmetry that we are seeing in the IV characteristics is coming from the PN junctions that is formed at the silicon MOS2 heterostructure. We also studied their transient response just to check their quality, and we found that the rise and fall times are pretty good. Actually, it's in a few tenths of microseconds in the range. We also studied their intensity dependent photocurrent, and what we found that as you increase the light intensity, it actually follows this power law. And what is the meaning of this power law? If the alpha value is close to 1, that means that as you are increasing the number of photons, your current is increasing on the same fashion, and it's almost, there is not much trap states are there. So alpha value close to 1 says that there is no loss of these photogenerated carriers. And it again shows that the interface is pretty good here. We also studied the two important figure of merits of any kind of photodetectors, which is responsivity and detectivity. What responsivity tells you that basically what is the current that you are getting out of light, for a particular power of light. And detectivity tells you what is the minimum signal that you can measure. It's basically limited by the noise of that photodetector. And this noise mostly comes from the dark current. So higher the dark current is higher the noise. So to get a good detectivity, your dark current should be as much less as possible. And what we found that at 10 nanowatt per centimeter square intensity, the responsivity is around 39 and detectivity is 4.17 to 11 joules. This is a reasonably good values for a photodetector. So once we're happy with this performance of our photodetector, we coat them with high dielectric material. So here we first took PVDFT RFE. Here we showed that this is the photo response before coating the PVDFT RFE, and after coating PVDFT RFE, the photo response is increasing significantly. However, one thing to note that the photo response keeps increasing as you increase the bias. I'll come to this point in a few seconds. We also studied the responsivity as a function of wavelength, and what we found that below 700, the responsivity actually increases significantly. And this curve actually kind of exactly mimicking the absorption curve of MOS2. So it does points that whatever the enhancement that we are seeing is because now because of the MOS2. So whatever the change happened that happened in MOS2. And also the reason is that we use a degenerately doped silicon, so which will not contribute to the photo response here. But one thing we found that the power dependence of photocurrent, the alpha value is now reduced. Earlier, for this device, before coating the PVDF, it was 0.93, but now it's 0.7. Now, the reason that we think is with increasing light intensity, it's generating a large number of carriers, but these MOS2s, their mobility is not that high. That's why the carrier collection is not that efficient. And that's the same reason where the current is increasing as you increase the bias more and more. So basically it's kind of collecting more and more carriers. So this non-saturating behavior is also kind of coming from the low mobility of these samples. If you look at carefully that in the low wavelength region, there is a upturn in the responsivity. Means your enhancement is higher in the low wavelength region. The reason that we think is that this is coming because of the effect of the deep trap state. When you coat a high dielectric medium, then what happens is that these deep traps become shallow traps. So now that helps to increase the photocurrent in the low wavelength region. And we also did a transient behavior, studied the transient behavior photo response over a large time. And we found that, yes, without dielectric, there is a very slow tail observed. But once you coat it with this dielectric, then the slow tail actually vanishes. So basically now it becomes a shallow trap from where you can easily, the carriers can get easily delocalized and they can contribute to the photocurrent. We tried a lot of other dielectric to observe this enhancement. Some are solid, some are liquid. And we found that in presence of very high dielectric material, high dielectric environment, the enhancement of photocurrent can be close to 3 orders of magnitude, which is, we think, is pretty good. So in summary, we have successfully fabricated this silicon monolayer MOS2 mixed dimensional van der Waals heterostructure, and we observe nearly 3 orders of magnitude enhancement in photocurrent in presence of a high dielectric medium. And the reason that we believe is because this high dielectric medium, screens the coulombic interactions and reduces excitonic binding energy, which helps separating the photogenerated carrier. And as a result, you're seeing enhancement in the photocurrent. So I should acknowledge these guys. We got the HBN from Professor Taniguchi. We also use HBN as a high dielectric medium. The optical measurements are done in Dr. G.B. Pavankumar's lab. We also did some theoretical calculations. It's actually done by Dr. Mukul Kabir to support our claim, and which is also kind of matching with our findings. And I should also acknowledge the funding support from ISAR Pune, ACRB, and CEFIPRA. Thank you for your attention.
Can you hear now?
Yeah, I can hear.
Yeah. So thank you, Dr. Rahman, for an interesting talk. Now the talk is open for questions and comments, if any.
Can I ask a question? This is Arindam here.
Sure.
Yeah, sure.
Adekur, what's the reason behind this large responsivity? Do you have effects of defects as well? Because there should be a lot of traps in this CVD MOS2, right?
You are absolutely right. Okay. This large responsibility, I mean, we believe that it's due to the effects of trap because, you know, I mean, this photogenerated carrier, if one of them gets trapped, say the hole gets trapped, then the electron, it cannot recombine easily. So basically, there is an injection from the outside circuit as well of this carrier. So that's why probably the responsivity is pretty high in this kind of devices. And similar thing observed earlier in case of nanoparticle during like 2010 or in that time. I mean, people observed this high responsivity in some nanoparticle assembly, I mean, photo detectors made by nanoparticle assembly. And I think the reason is the presence of trap states. That's right.
Okay, thank you.
Any other question? Okay, if there are no more questions, let us thank Dr. Rahman for a very interesting talk and for finishing the talk very much in time. So our next speaker is Dr. Prasanna Sahu from IIT Kharagpur, and he is going to talk on 2D lateral structure control growth challenges and optoelectronic applications. So may I invite Dr. Sahu to give his talk.
Yeah, can you see the screen? Hello.
Yeah, it's
yeah. Thank you very much, Prasanna and the organizing committee for inviting me for this conference. They were nice talks. So today I will talk more on the growth aspect based on the scope of the conference and the particular section. So I will give more emphasis on how to make heterostructures. There are vertical heterostructures are easy to fabricate, but however, how we can make atomically, how we can stick atomically different atoms to form a lateral heterostructure. That is not possible otherwise by a mechanical exfoliation process. This is only possible by CBD or growth process. So here I will show in this lateral heterostructure how we can control their growth in a more easier way, and also it depends on the time. So I can cover some of the application aspects of this kind of lateral heterostructure. Okay. So the bigger picture is why we need another type of ultra-thin material, because of electron is becoming flexible. Now we are all are more passionate for using transparent semiconductor, high performance, ultra-thin body, and definitely their performance should be better. So in addition, you can see we have all around us, there is a pool of a Wi-Fi signal, whether we can harvest this kind of Wi-Fi signal into cell power our small scale electronic devices. So for that, the MIT group, they have done this metal to a semiconductor metallic phase junction. They could able to show a demonstrator that it is possible indeed to convert the Wi-Fi band radiation into electrical DC current. So in bigger picture, we can see that there is increasing demand in incorporating more number of a transistor in a semiconducting component. And more likely by 2030, this is the transistor and neuromorphic computing is going to dominate the market, and for which two-dimensional materials are more important because three-dimensional semiconductors have suffered badly when we decrease their channel width while making them as a small channel devices. You can see here the silicon-based or other gallium or the 3-5 semiconductor-based, most of the materials, their electronic mobility decreases drastically below critical thickness limits. Whereas if we check the conventional, this two-dimensional material from MOS to WSC2 on this kind of materials, even if their body thickness is less than a nanometer, they have reasonably good mobility. That's why these are a promising candidate to be incorporated in silicon along with silicon-based electronic devices. With that, there are already very good talks on layer materials. I'm not going to introduce what is this layer material. One important point is when we are reducing the thickness, this metal become direct band gap because we can see the K point. There's a transition from our measurement. We can also see if you have one layer, this will give a strong emission. And if you go to the reduce down to the bilayer or tri-layer, their emission intensity decreases drastically. So because of this band wall gap between this material, it is easy to fabricate in mechanical extrusion process. However, it is not possible to make lateral heterostructure by mechanical extrusion process. Okay, so in addition, this material, you can see the band gap value, whatever I discussed. You can see the many MOS2 in the bulk, their indirect band gap in when you are moving to thin down to a single layer. So most of them, these 2D materials, they form that their band gap increases and they form direct band gap nature. In addition, they have also very interesting degenerative valley states, the degenerative valency band states, where because of that, there are many new promising aspects like electronics, valley Hall effect. All these things are possible using this kind of materials. Okay. So another exciting physics in this material is exciton. Our previous talk we already discussed about this formation of a monolayer. In monolayer, we can see because of the reduced dilating skinning and strong coulombic interaction, the exciton binding energy is stronger. This is good if you want to use exciton as a carrier for any of your electronic devices. So in the excitons are good that they can freely move on the surface, because that's why it is possible to make to harvest, because their binding energy sometimes can reach half electron volt in this material. And also for a monolayer, the absorption process absorption is almost 10 to 20%. That's why even if their material body is atomically thin, it can be used as a potential candidate for photovoltaic and light emitting devices. In addition, these excitons, because of their strong binding energy, they can also combine with the other kind of carrier. They can form charge exciton, sometimes called trions, or bi-exciton we can form. That also under high magnetic field or things, one can form this kind of bi-excitons. These are potential candidates for observing superconductivity and superfluidity in materials. Also depend upon the type of substrate one can use. One can also form polarionic trion with a rotational orbital of phonon mode can combine. That can also form trion. That means we have enormous possibility to tune the excitonic states in this kind of 2D materials. One also have already demonstrated one can make switches using this kind of excitonic materials, where we can shine laser with a vertical stacking. One can make switch out of it. And very recently, And there is also new physics are emerging where you can stack one metal with other metal. You can see there is a formation of artificial lattice, and that can effectively trap particular excisions that can be a source of many interesting physics. So one can see by adjusting the rotational angle, one can vary, we can tune these phases, artificial phases. Okay, so before going to talk on heterostructure, it can form different types, type 1, type 2, type 3, and especially in atomical thin sample. So in bulk materials, because when you form a PN junctions, so there will be extended depletion region. But however, since these 2D materials, their physical dimensions already in this limit, atomical thin limit, there is most of the charge transfer are governed by the tunneling process. That's why the ultra fast charge transfer can be realized in this kind of stacking. And this challenge, much more interest in this field community is one can form many different kind of heterostructure by selectively choosing appropriate combination of a material. So one can see from a nice arrangement of this table. So, however, until now, this kind of 2D materials or heterostructures are suffer drastically because of the poor quality materials as well as limitation in aligning them in a specific manner. So that's why in terms of photovoltaic or electroluminescence devices, their performance are far below the theoretical values. That's why there is still ample room for further improvement for the device prospect. With that, my plan of talk is, so I will be talking about how we can make this kind of lateral heterostructure where we can atomically stack atoms in a lateral or in plane directions, how we can integrate them, this kind of structure, not only in one monolayer, whether we can make bilayer or we can make 2D, 3D integrations. So we can change their phase, we can tune their charge, valley spin. With that, and from the growth cells, I will show you how we can make this kind of structure in a very simple, reliable, and also scalable process, CBD process, how we can make control this kind of atomical stacking in lateral directions. And also we'll see in situ how we can light matter interaction, how we can interesting charging and discharging kinetics occurs in this kind of lateral heterostructure. So also in some exciton-based imaging, nanophotonics, and in time format, I will cover briefly about whatever the heterostructure we fabricate. So they are also promising material for nanoelectronics, for observing room temperature, light emitting diode, and also solar cells. Okay, so that means also there are many new physics can emerge in this kind of materials if we can combine different aspects like charge, spin, and valley. If we combine their phase together, there are many more new discoveries are awaiting in this class of material. With that, I am now going to ask more on growth of these materials. What are the recent challenge was? So several years back, there are worldwide effort to make this kind of lateral heterostructure. However, all these processes like single step, two step, pattern growth, they were not scalable. Even though the first paper published in 2014, the field was not expanding because of the limited knowledge on the exact role of exact growth mechanism and also their stability. So recently, so we discovered a way that water vapor and using simple by controlling the carrier gases, we can tremendously control the type of materials that we can grow and along the lateral directions. One can see that here. It is like you can very star shape. We can control this molybdenum. Then tungsten, we can see a fine line. Then again, tungsten, molybdenum, this kind of lateral conformal growth along the lateral plane. Not only monolayer, we can also make superlattice in a bilayer superlattice together, which is otherwise not possible in a CVD process using other techniques. only if in previous times or people will realize superlatives using MB or emulsibility kind of technique. But here, with a simple CBD technique, one can also make this kind of superlatives. I will discuss about that. The future is also, of course, demand along with the 2D, whether we can control their three-dimensional confirmation, three-dimensional growth. Okay. So here are simple methods. CBD, which is a very is a scalable process, low cost, and also one can tremendously control their stoichiometry in this process. In our method, we have simple two-zone CBD furnace where you can put your material at a high temperature zone. You remember, if you want to grow molybdenum selenide tungsten selenide based lateral heterostructure, you have to put their raw powder there. Then by controlling the carrier gas, one carries some amount of water vapor, another is sometimes we call oxidizing gas, and this is reducing gas. So that's effectively controlled selectively like a valve or something. It can selectively evaporate one material at a time, and you put a substrate at a lower temperature, and there it can grow. So basically it's a solid vapor reactions. Once a nucleation site form, then these adatums from the vapor phase, they can come and attach on these edges because since these are van der Waals materials, the top surface are saturated, there is no free bond. If it is high quality material, definitely there is no place for the atoms to stack. That's why they roll down to the edges. This is how it can form a bigger island. So now another more complicated step is how we can realize these lateral connections. So here in the simple in this diagram, you realize that so when you flow some amount of water vapor in this chamber or CBD reactor, this favors only molybdenum component. Molybdenum X then means this can be selenide or sulfide. So the moment when we suddenly stop the flow of nitrogen to reducing gas, this quickly deplete the surface of the precursor on this molybdenum growth, and it starts formation of the WS2 domain and the existing edges of the initial MO2 domain, because these are the lowest energy or the active site for the incoming adatom to grow easily without forming another new nucleation site. That potential need more higher activation energy. That's why it can more easily find a place where it can grow. And the moment you switch between these two states, then you can form again molybdenum, tungsten, molybdenum, all are connected laterally like this. Okay, so we can see a very single crystals of in the same image in the direct contrast between molybdenum, tungstens, and we can see very uniformly or conformally they grow and in the triangular shape. Going more deeper to probe the exact growth mechanism. So imagine in the first growth step, it's called oxidation step, we say you have raw material of molybdenum and tungsten. The moment you interact with the water vapor, what happens because of this is reactive faster with the water vapor, it will form a molybdenum dioxide compound, on the surface. And this compound is very volatile, and the moment it interacts, it can reach from the surface and contribute to the growth at the lower bottom side. However, the tungsten is very peculiar, and when under the presence of water vapor, this is a stable compound, and it is keep building of the higher suboxide phases. You can see many suboxide phases it can form. So that suboxide phase don't contribute to the growth. Only MO2 contribute to the growth, and this is how it can form. When you suddenly switch from stage 1 to 2 in the presence of reducing gas, you will remember the moment these are very volatile, the moment it form, it immediately leaches out from the surface. When you are again putting the reducing gas, it is suddenly deplete this MO2, whatever residual MO2 are there, and it will form a molybdenum or metallic layer. Metal will not easily evaporate at that particular temperature. However, there are tungsten suboxide phases that at that high temperature with hydrogen help to leach from the surface, and that can contribute to the growth. At the same time, this can reduce to tungsten, and at the same time, since they have a lot of preserved oxide phase that were preserved during this process, now they started contributing to the growth. That's why it's very interesting mechanism happens during the formation of this growth. And if one can tune the exact width by allowing the time. So how much time one can keep to interact this compound with the water or hydrogen, that determine width of the particular section. So by changing between stage 1 and 2, we can form this kind of lateral conforming growth of these things. Not only that, so as I told, one can also control the kinetic factor, because so you can imagine from monolayer to bilayer, so there is a barrier at the interface where the atom will find the higher energy side will not go to the top. And also, but if you have, you can increase the substrate temperature a little bit higher, so that we reduce the barrier from the initial island, and also that can promote bilayer growth, bilayer of individual domain. So in addition, sometimes what happens if you increase the temperature as well as higher the flux amount, matter or precursor amount, so one can control the domain size, or one can control bilayer or trilayer, and still we can maintain the growth in the lateral directions. Okay, so now we'll go show you, demonstrate how to characterize this kind of structure. One can see like 300 micron size up to one can make this kind of lateral junctions in this way. And with a detailed Raman and a PL, one can characterize details how this domain are present in this section. You can see here, suppose, and this bar determine how much time we interacted the compound. You can see it is very fast. It's only 2 minutes. It can grow this much size. This is 10 micron bar. So it can see more than 5 micron or island, 10 micron island it can form within 2 minutes. Oh no, sorry. So its extraction to is nearly 7 minutes. It can grow 10 micron area. So then, but the tungsten growth rate is faster. Within 1 minute, it can grow 2 micron. So like that, you can see how fast the reaction rate is here in this particular growth condition. And in this particular whatever optical image you can see here in the PL intensity map, one can see whether how these domains are spatially connected to each other. There is no formation of alloy in between. So however, if you check the interface, because that is also important if one want to make use of this material for transistor. So the nature of interface is important. For that, we did the line mapping to take PL spectra along this line and make a contour plot with the position distance from the center towards the edges. You see how these are alternatively changing. What does that mean? When you are changing from MOS to WS2, this interface is a gradual shift in the PL. That means it is forming some alloys at the interface. Whereas there is an abrupt change when you are changing from WS to MOS2, that means these materials are spatially isolated. There is no alloy, or the quality of interface are better. That is further confirmed by the head of STM images, where you can say that whenever you have this kind of transition from WS2 to MOS2, then we have a very sharp interface. And that we can confirm sometime from the line map itself. We can correlate the diffuse interface and sharp interface using this from this line map. Same way, we also can fabricate also on WS2 MOS2 heterostructures, and that form different kind of truncated triangular shape because of the different growth rate along different facets. And also it is sometimes interesting that because a lot of magnetic, I can see many speakers from magnetic community, there was some paper also that theoretical predicted. So, so one can, depend upon the termination, one can induce magnetism in this kind of materials. Okay, so another step is, so as I told, bilayer are recently a very interesting topic of interest because that can host a wide range of excitons, intralayer excitons, and that also because their energy are different, so one can effectively tune their tunes for specific applications. And also bilayer can form different polytypes. One can form, you can see different polytypes in this material. They have slight different energies. In addition, in bilayer of MOS to WS2 heterostructure, one can form, you can see WS2, there is a indirect contribution, and still the direct band gap contribution AX is still dominating, even though it is direct, is a bilayer. And also in MOS2, you can see both in the room temperature Raman PL spectra, still the PL spectra is dominated by A and B excitons. So there are, that we can see here the band diagram. So that's why the bilayer, and one can selectively tune or excite particular frequency or particular emission wavelength depend upon their particular specific application. We detail characterize again their interface properties. All these you can see how fantastic a way we can make this kind of bilayer using the simple substitution methods. Okay. So how about, because how about the possibility to expand this field, because your basic component MOS to WS2, these are limited. So there is internal, you can see that internal energy of mixing between MOS2, MOS2 is minimum, so that it can these components are completely miscible. One can see from these band structure. So where you can see that by selectively changing from MOS to MOS2, one can tune the emission wavelength in this class of material. Exactly, we did the same thing in our method by selectively using different heterogeneous precursor from point of chalcogenides. So C2S2, by selectively choosing, we can also make we selectively tune or retain the composition of individual alloy domain, and still we can retain the lateral configurations. So we can see again from the PL line scan, they are very well controlled, and each individual composition can be retained in the lateral configuration. And in addition, we recently work also, we can see how systematically you can tune the band positions at the interface between this kind of alloy heterostructure. Okay, so we, in addition to PL, we can use second harmonic generation to map this kind of lateral heterostructure. Second harmonic generations are nonlinear optical processes that allow materials which have inversion symmetry breaking. So if you see the monolayer is a bilayer. TMD, that's unit cell is like that. For a monolayer, there is a breaking of inversion symmetry. That's why you can get strong second harmonic emission from monolayer. For bilayer, they cancel out and we cannot imagine. So in second harmonic, a laser beam with frequency omega excite the samples, and it can generate a 2 omega. That's why you can second harmonic. And this has been used people to characterize the layer number. One not always go to TM to verify or AFM. One can use the second harmonic generator to check the sample layer number. We can see that two layer even number layers they are in the SS signal are diminishing, whereas odd number layer one can get probe A exciton and B exciton peaks in MOS2. Also, they can also get the binding band splitting from this SSG mesh. For our method with collaboration with our Brazilian group, so where we can see that this lateral heterostructure, the intensities are coming at the interface. This is the electric field intensity, sum of this part and other parts. And in intensity at the interface, in addition, the component coming from your molybdenum tungsten domain, there is another factor gamma, which is really on the phase difference coming from different materials. That phase difference can be from crystallographic orientation or different crystallographic geometry, or it can be from susceptibility of both materials. But for our case, because these are laterally connected and they have nearly similar crystal structure and they're oriented, so this factor is mostly coming from the susceptibility of different materials. So in the next slide, we can show that using the SSG mapping, we can by tuning the by mapping is done by the emission wavelength. By excitation wavelength is different, is half of that. So we can show that at 425 nanometer emission wavelength, mostly the tungsten domains are brighter, and at a 550 nanometer, the molybdenum domains are brighter. You can see that here. However, in between around 440 nanometer, the tungsten and molybdenum domains, they have a nearly similar intensity. However, at the interface are now brighter. That means there is a somehow constructive interference happens from the signal originating from the tungsten and from the molybdenum side. And from the polarization difference SH imaging, we can see that how relative orientation of different domains in the structure, and that we can see from the formation of the well overlap of 4-petal pattern, that indicating all the domains are crystallographical oriented in a similar direction, and the interface intensity is enhanced. And this is because, to prove that why it is enhanced, so what we did it, they did it, our collaborators said they can block one of the, in the PMT, one of the block partially, and they found that because of the blocking, there is no interference forming at the interface, and that's why the intensity gradually decreases. So that because of the enhancement, we conclude that it's happening because of the constructive SH interference at this interference. But interestingly, what we saw in mostly in case of MOS to WST monolayers, so we have similar monolayer, we saw the enhancement, but there is no constructive interference happening at this income monolayer. But still, surprisingly, we can see in a bilayer, we still can see a strong enhancement, we can still see strong SH signal, which is surprising, it should not happen. But most likely further experiment can confine, but we propose that. So maybe it is due to the A stacking, but in the MOS2 or WS2 domains, they were mostly AB stacking. That's why, yeah, we can able to see that. Okay, so yeah, this part I'm skipping with interest of time. What is interest is that because we can also make superlattice, fine line of more than less than 100 nanometer. So we can make this kind of superlattice with near field imaging. So what we can do, we can make a laser light and use a PL imaging, whatever at the apex of the tip, there is a strong enhancement or a coupling of the light that enhances the PL emission. From that, we can characterize details. You can see a 200 nanometer, a small section we can image or in terms of photoluminescence. And is there any heterogeneous effect or there are degradation?
Dr. Sahu, you have 5 minutes more.
Okay. So there is another method we can grow this kind of structure, is a laser assisted, where you can put a laser light and we can convert local material to the other materials, because that we can, yeah, this is, yeah, there is a, we can see that when we are shining laser light, so we can convert initial in reducing atmosphere H2S, you can convert MOS2 to MOS2, a material from lower energy to higher energy. And we with the in situ Raman spectroscopy, we can see how the other peaks are emerging from these two sides. So we calculated details, time scales involved in that process. With further, and now I will go to the more device part. So why the 2D materials more advanced is because they have lack in dangling bond. We can easily control these, control the carriers, which is like or a small applying a small gate voltage. So okay, so so what we see that so that in MOS2 WS2 domains with a device we fabricated, this device can characterize MOS2. So what we can see the WS2 from the transport curve, WSC2 if you measure from 2 and 3, it is mostly showing P-doped type, and MOSC2 is showing N-doped type. That means by our direct growth, we can directly grow PN junction without additional doping other things. That's a tremendous progress in this field. We can directly grow PN junction. We know when we have a PN junction, when we shine light with increasing power, that increases the current, photocurrent. That is a signature of showing diode-like response or amplifications behavior, and we get reasonably good on-off ratio using this kind of lateral heterostructure. However, in monolayer, we didn't see the photovoltaic effect, but in bilayer, we can see similar PN junction behavior. And what in addition to photoresponse, we observe the photovoltaic effect because of the short circuit current at 0 gate bias voltage upon exposure to light. So also, yeah, I'm skipping this. Okay. So what we found here in photovoltaic, the efficiency is lower in many people. In vertical geometry, the area when calculating photoconversion efficiency, one choose the area of the whole PN junction region. But in lateral geometry, if you will consider only this region of one dimensional chain, then our photoconversion efficiency is enormous. That is not possible. That's what we changed. We checked we could different gate length of the junctions. So later on, with the addition, we got maximum photo conversion efficiency of 0.08. But if we check, we choose the depletion width is many. If you consider from other data, so we can get a photo conversion efficiency of around 2%. Okay. So in terms of LED, in photovoltaic, you shine light and you get emission, you extract the current. In electroluminescence, you apply voltage and you inject current towards the junction and illuminate. But in this, we also saw that a strong luminescence around the 1.94 eV, which is close to the A exciton peak of a WS2. So in principle, we should supposed to get a strong emission from the interband, like in this junction. But the reason is not clear. That's why, because there is somehow there is a carrier or mode dominated or transport to the other side of conversion happens or something in that our process, and we get a strong emission only on the WS domain, no matter with using a monolayer domain. You know, to further evaluate what exactly happened. So there is a collaboration with another group. What we see how the exact charge transfers occurs between in this bilayer geometry from molybdenum to tungsten. So using a near field scanning microwave impedance spectroscopy, which effectively measure directly the local intrinsic as well as photo-excited free carrier by using a tip sample admittance, whose value G plus I omega. Okay. So in this microwave signal is corresponding to the capacitance or conductance. From that signal, you can see here what we can measure that you expose light of a different wavelength or energy, so we can probe effectively how molybdenum domains are charged or free carriers are increased when it is the edge of the absorption threshold of at A exciton around 1.82. We can see the molybdenum domain are fully charged, but still there are some discernible charge we can see on the WS domain. One should not see any charge on the WS domain, but we can see that. That means there is some charge transferring from MOS to WS domain. By increasing the energy of excitation, so or exposure, one can see the whole surface of charge. And you can notice that in the bilayer domain here, bilayer are fully charged and monolayer charging slowly. Because bilayer have more free carriers, that's why they can charge fully. So what interesting is we can charge sometime, this residual charge sometime can be seen for 72 hours. That's a lot of, when we are making photodetector or something, people have to understand that residual charge, once excited, they can still retain on the surface for a longer time. So in order to prove that, what you can expose the surface with the 20 minutes, you expose with the laser light, you can fully charge it. And this is a bilayer domain, this is a monolayer domain. And we switch off the laser, we can still, this by residual charge still retain on the surface. That you can see from the time domain map, and this from the mapping from the selected region here. So you can see this residual charge can be seen from longer time. So with that, what we can conclude is, when we are shining light, the molybdenum domain somehow are charged first in the beginning, and from that charge will transfer to the WS2 domain. And since we are exciting below also, below the threshold A exciton energy of the WS2. And because we conclude, because when we choose pure WS2 domain, we cannot see this charging behavior. Only in MOS2 we observe this charging behavior. Further studies are ongoing to understand more detail of the process. Okay. So with that, we can see that most of the in terms of power conversion efficiency, this is very less as compared to the more theoretical predicted values. So, however, in power density, one can see the amount of material energy one can convert with the amount of material is enormous. That's why still there is a bigger possibility to improve this performance. One can do compositional tune and the material to absorb many photons, or sometimes one can engineer or different heterostacking with a different geometry of graphene. One can effective carrier separation can be achieved. Okay. So with that, I can conclude that CVD method is a very powerful technique which can control not only the large area of TMD material, that also can be used for selective growth of TMD domains and also for over control over layer number. And also this material can be useful for low power optoelectronic devices. And I acknowledge my colleague from our group where I did most of the work in the first work on this US, and also my colleague here in Cambridge group, and also collaborators. And also I acknowledge my group. We have just started our family in IIT Kharagpur. Okay, thank you very much. I would be happy to answer some of the questions.
Yeah, thank you, Dr. Sahu, for a very informative and illuminative talk. Now the talk is open for questions and comments. Is there anyone having any questions? Okay. Okay, so if there are no questions, then let us thank the speaker once again. And we'll move on to the next contributory talk, that is by Dr. Kapil Borkar. He is at Greece and University of Reims in France. And he is going to talk on simultaneous synthesis and transfer of graphene on PDMS using novel laser-assisted method for application in self-powered tactile sensing. So his talk is going to be for 15 minutes. So after 12 minutes, be for question answer. So I request Borkar to confine his talk for 12 to 13 minutes. Okay. Okay. So
yes.
May I invite you to the talk?
Thank you so much. So I hope the screen is visible.
Yeah.
Yeah. Thank you. So hello everyone. Thanks for joining. I'm Kapil Borkar, final year PhD student, and I'm going to tell you a technique how to simultaneously synthesize and transfer graphene on any desired substrate. As a proof of concept, I have deposited it on a PDMS for self-powered tactile sensing. And let me start by showing you this picture, which summarizes important milestones from the journey of room-sized computers to small microprocessor chips. This journey was challenging, but the future of devices is even more exciting, as the future devices not only have to deal with beyond the Moore's law technology, but they have to be flexible, power efficient, and scalable at the same time. In this regard, self-powered devices harvesting energy from the ambient conditions seems promising. The devices that work on piezoelectricity and triboelectricity are of great interest because of their small sizes, low cost of fabrication, ease of fabrication, and along with this, the possibility to transmit the energy wirelessly. These devices has applications in IoT sensors which need small powers, and in biomedical applications and sports sensors. Particularly Teng devices has gained a lot of attention, as along with their applications, the performance of these devices in 2012 was around 3 watt per meter square. And just within a few years, this number has gone beyond the 2000 watt per meter square. So what exactly is Teng? Teng devices can be fabricated in one of these 4 geometries. But when it comes to attaching a Teng device with human body, the single electrode mode is the most studied one. And the single electrode mode is the most studied one. And you can attach this single electrode tank device either as a wearable or as a textile to the human body. So what exactly is single electrode tank? Single electrode tank consists of at least one tribomaterial and one electrode. The human skin acts like a second tribomaterial for these devices. In order these devices to perform well, they have to be flexible, efficient, and scalable. Along with this, the most important factor is they have to be conformal with the skin or human body. As you can see, these devices has one tribomaterial and one electrode. There has been various studies where people has tried and tested different tribonegative polymers like PTFE and PDMS for the application in tank devices. Further, it is known fact that the surface modification of these polymers enhances the overall performance of the device. Whereas when it comes to the electrodes, starting from different traditional metals to the more complicated silver nanowires has been employed for collecting charges efficiently. Of course, there are some drawbacks involved with collecting the charges. In recent years, graphene derivatives has come up as one of the most potential candidates for collecting these charges efficiently. As we all know that graphene synthesis started from this easy Scotch tape exfoliation method, which gives really excellent quality of crystals. But this method is absolutely impossible to industrialize. And hence, since then, there has been various methods developed, which are mentioned in this table. This table also clearly showcases the drawbacks of each method for the quality of graphene grown. Along with this, the high temperature growth and the specific chemicals required to transfer graphene from the grown substrate to the desired substrate makes it complicated processes and CMOS incompatible. Hence, in this regard, laser-assisted growth has come up as one of the most promising solutions. In literature, what usually people do is they use CO2-based lasers for irradiation of polymers, and with these, you can graphitize the top surfaces. Researchers has already tested different carbon-rich precursors like polyimide, cork, and other polymers. These techniques are commonly known as laser-induced graphenes or laser-induced forward or backward transfers. Although this method has a possibility to scalable the growth, but only it graphitizes top surface, and you still has to perform one extra step to transfer the graphene grown from the polymer to the desired substrate. Also, if you compare the quality of graphene grown on different polymers, only Kapton gives the good quality of graphene. It is absolutely necessary to take extra precautions while using CO2 lasers, and it is expensive as well. Recently, Smith et al. Has performed an experiment with laser where they use a triazine as a sacrificial layer for transferring a CVD grown graphene from the copper substrate to the desired substrate. This is the only work which has used laser for transferring graphene from the copper substrate. But there are no work which reports the simultaneous growth and transfer of graphene using laser. Hence, what we propose is instead of using a CO2 laser, we use NdArc laser, which is common tabletop laser, and we shoot our precursor with this laser. With this method, you not only graphitize the top surface and bottom surface of your precursor, but you simultaneously transfer the graphene from the precursor to the desired substrate. The best point about this technique is you can absolutely use any precursor, carbon-rich precursor, including polymers and resins or other carbon-rich sources. You need only 1064 nanometer laser. It is a millisecond laser, so you can actually have a large area growth at very fast speed. We believe that there is an explosive nature involved which drives the graphene from the precursor to the desired substrate. And hence, we call this method as laser-mediated explosive synthesis and transfer. You can use absolutely any substrate for transfer. And as you can see in these below pictures, we use carbon paper, molybdenum foil, glass, PDMS, and various other polymers for transferring graphene. From now onwards, I will speak about mainly the krypton as precursor for transferring graphene. When we irradiate pure krypton foil, we can achieve the pure graphene as a growth material. Whereas when we use krypton along with the silicon glue on top, we have achieved a nanohybrid of graphene with SiOx nanoparticle inside. This explains if we choose our precursor wisely, we can make nanohybrids of nanomaterials with graphene at one step. Along with these, we can pattern the graphene growth and make directly the interdigitated electrodes on desired substrate. As you can see in these SEM images, they are highly porous three-dimensional interconnected structures with very efficient sheet resistance of around 130 ohm per square. Further, XPS was employed to understand the final product. As XPS sees, we have achieved the highest carbon to oxygen ratio around 30, which is not reported previously by any laser processes. Let me clarify this, that krypton has almost 7% of nitrogen as a element, but we see no nitrogen in the final product of the graphene, and this confirms that our transformation is completely successful. We employed Raman spectroscopy to further confirm the enhancement of sp2 to sp3 ratio, and we see that there is a very narrow peaks with very small full width half maxima, which are typical. Along with the typical vibrational modes of graphene, we also see the turbostatic modes. Turbostatic graphene has a better quality of electrical performances than the Bernal-Stack graphene. To confirm this turbostatic nature, we perform TM analysis, where in above images, you can see that the few layer graphene structure, and the below images, these are the SiOx nanoparticles embedded in a graphene. Bernal-Stack graphene generally has a interplanar distance of 0.338 nanometer, whereas in our case, the interplanar distance is always more than 0.349 nanometer. As a proof of concept, we deposited these two graphene electrodes on PDMS for tactile sensing. This is the device where we use PDMS and human skin as tribomaterials and our graphene electrodes for collecting the charges from triboelectricity. We employed this simple finger tapping to mimic the normal human body motion. As you can see, when we use a graphene with SiOx nanoparticle as an electrode for collecting charges, the open circuit voltage generated was around 35 volt peak to peak. Whereas when we use a pure graphene, this open circuit voltage was around 65 peak to peak. Short circuit current was also measured by connecting different resistors in series with a device, and we see that both the devices follow the similar trend. The most interesting fact is we find the maximum output power of this device across 3 megohm resistor. It is a known fact that the output power is maximum when we have internal impedance of a device matching with the external load. For real world application, it is absolutely necessary to have as less as possible the internal impedance. And as per our knowledge, this is the lowest internal impedance reported for any single electrode tank device. We believe that this is due to the graphene electrodes. And let me show you a small video where this is our device where the black area is the graphene deposited, and this is the only active area of whole PDMS size, which is 1 by 2 centimeter. We tap this with a simple fingers, and we could light immediately the LEDs. So finally, I would like to conclude that we propose a novel method of synthesizing graphene, and with one step, we not only synthesize but transfer graphene on any substrate, including polymers, or if you choose our material wisely, we can deposit graphene with nanohybrid nanoparticles, and we characterize our material, and we see that we do not compromise with any of the quality of graphene. And finally, as a proof of concept, we deposited these graphene electrodes on polymer, PDMS polymer. We tested this device for 5,000 cycles over 4 months, and it performs quite well in ambient conditions. We could immediately light LEDs with simple finger tapping, and this is the lowest internal impedance reported for these devices. Although we have shown that the application in tech device, this technique is quite useful for other research fields where we need direct coatings of graphene or energy related applications, membranes and filters and so on. We have already submitted this paper for publication and applied for the PCT patent. And finally, I would like to acknowledge organizers for giving me opportunity, my supervisor, and of course, the funding agency, Mary Skłodowska-Curie Action, for funding this work. Thank you.
Okay, thank you, Dr. Bhorkar, for the interesting talk. Now the talk is open for questions and comments. Is there any questions?
Hi, Kapil. Can I ask a question?
Yes, please.
Sure.
Hi, Kapil. It was a nice talk. So, question is, so what, and maybe, so is the your process energy dependent? Laser energy dependent? Is the quality you were talking about?
Yes. So, for example, we have tried different fluences of lasers, and we could find that around 74 joule per meter square is you get the best quality of graphene. But even if you move a bit, like if you go a bit aside of this, either plus or minus, the quality does not decrease to a big extent. So, but yes, the optimum condition is around 74 joule per meter square.
Okay. So in slide number 12, you have compared responses from the deposited graphene versus what was the other electrode material you used?
Graphene with SiOX. So it's a graphene with SiOX nanoparticles inside.
Okay. So the response you have compared with what? The other with the lower response?
So we have compared the two graphenes what we grow. One is the graphene grown from pure Kapton, which is pure graphene, and another one is graphene grown from Kapton with a silicone glue on top, which gives the graphene SiOX nanoparticle. Okay. So we were just yes.
Yeah. Okay. Thank you.
Yeah.
Any other question?
Can I ask one question?
Yeah,
okay.
Sure. Yeah.
Yeah. So, are you always getting a monolayer of graphene? I mean, or you don't?
No, this is not exactly monolayer. This is more like 3D interconnected structures. So it's difficult to say it's a monolayer graphene because it's.
You have not characterized it, I guess.
Sorry.
You have not characterized it, have you?
No, if you see the TM images, there are some portions where we see the single layer of graphene, but other places are more few layer of graphene. Let's say it's a 3-dimensional sponge-like structure. Honestly speaking, so it's more difficult to say. Yes.
Don't have the uniformity over the. And what area? What is the area you are doing? I mean, you said that it's large area, right?
Yes. So, for example, we can absolutely grow a centimeter square within a minute or so, and
that doesn't give the uniformity over that area. 1 centimeter square, you don't get that uniformity, right?
You mean the single layer of graphene?
Yeah.
No. It's absolutely not possible to get a single layer of graphene with laser methods, because most of the times when we use laser assisted growth is a explosive technique where you actually decompose your precursor. So you do not get this. You cannot compare this with CVD grown graphene where you have very good, let's say, epitaxial or absolutely 2-dimensional material. So this is more like a 3-dimensional material with few layers of graphene.
Yeah, I would expect more few layers of graphene than monolayer. That's the.
Yes, exactly. Yes, you're right.
Okay,
yes.
Thank you.
Yes.
Okay, any other question? No. Okay, if there are no more questions, let us thank Dr. Kapil once again for the nice talk. And now we move on to the next speaker. is Dr. Akash Mahapatra from IIT Madras. He is going to talk on Raman optothermal studies on CVD graphene layers with rotational stacking faults. So I invite Dr. Mahapatra to give the talk.
Thanks, Professor Nigam. Is my screen visible now?
Yeah.
Hello everyone. This is Akash from Department of Physics, IIT Madras, guided by Dr. Manu Jaiswal and Dr. M.S. Ramachandra Rao. Today I'll be talking about our work on Raman optothermal studies on CVD graphene layers with rotational stacking faults. First, I'll be briefly discussing about the thermal properties of graphene. Well, graphene is a very well-known material in terms of its all intriguing properties. One of them is a superior thermal conductivity, which is in the range of 3000 to 4000 watts per meter Kelvin, which is even higher than the best bulk thermal conductors like graphite and diamond. Now, which makes it one of the strongest contenders for thermal management applications. Now, in order to understand why the thermal conductivity is so high, we need to talk about its phonon dispersion relation. The figure over here shows the phonon dispersion relation of graphene. It consists of 6 phonon branches, out of which 3 are the acoustical phonon branches, and the other 3 are the optical phonon branches, which are the high energy phonon branches. Most of the heat in graphene is carried by these acoustical phonon modes near the zone center. This is due to the high group velocity associated with these phonon modes. Now, out of all these acoustical modes, the GA phonon modes mostly carry the heat. I mean, for a single layer graphene, as is shown in this figure, nearly 70 to 80% of the heat is carried by these, GA phonon modes, and that is due to the high density of states associated with these phonon modes, along with a symmetry-based selection rule, which prohibits the scattering of these phonon modes, and hence they, contribute as the dominant heat carriers in graphene. Now, this sort of makes it quite interesting, for as far as thermal properties of graphene is concerned. This can be prepared using several techniques. We prepared the samples using chemical vapor deposition technique. In place of traditional precursors like methane and hydrogen, we chose solid precursors like camphor, whose Raman spectrum is shown over here in this figure towards the left side. It has these prominent modes, as you all know, the G peak and the 2D peak, whereas the 2D peak carries the information about layer number. In our case, it was quite surprising to see always it had a signature of a few layer graphene, whereas the thickness obtained from this growth was obtained to be around 15 nanometer from the atomic force microscopy topography imaging. Now, that was quite surprising to us in the beginning. When we compared it to the mechanically exfoliated graphene samples of even lower thickness around 9 nanometer, which had this signature of multi-layer graphene. So we thought whether these samples would be having rotational stacking faults in them. So in order to understand it better, we carried out selected area electron diffraction studies on it. We carried out these measurements at various locations. Whereas the figure B shows the result at one of the locations marked in figure A. It showed 3 sets of diffraction spots with hexagonal symmetry rotated with respect to each other at certain angle. Now, this sort of confirms the presence of stacking faults in our sample. The schematic in the right-hand side shows 3 individual graphene layers which are rotated with respect to each other at 30 degrees of rotation angle, and shows a beautiful formation of moire patterns. But in our case, these are not individual layers which are rotated with respect to each other, given the film thickness is around 15 nanometer. These are individual crystallites which are rotated with respect to each other. Now, similar work was carried out by Kalita et al., who followed the similar growth technique, and they also found the presence of stacking faults, rotational stacking faults in their samples, and they carried out this HRTM studies and also showed these diffraction images are shown in this figure, along with the presence of Moire patterns as shown in this figure C. Now, then we thought of, it's sort of interesting to study the thermal properties of these samples. We chose Raman optothermal technique. I'll be briefly discussing about this Raman optothermal technique, where we choose, we shine a laser onto the material, which acts as a temperature heating source as well as a temperature sensor. Now, in our case, as it is graphene, we chose the G peak as the prominent peak and studied its shift as a function of incident laser power. All that we need to do is, to obtain what is the temperature rise as a function of incident laser power, we also need to calibrate this G peak shift as a function of exterior temperature variation by putting the samples into a thermoelectric cell and varying the temperature externally, and recording the G peak shift. Comparing these two gives us the experimental temperature rise of the sample for a given particular incident laser power. We carried these measurements for mechanically exfoliated graphene as well as for CVD grown samples, and the results are shown in the slide. We carried out this G peak shift variation as a function of temperature as well as laser power. Now this G peak shift as a function of laser power we carried out using two different objectives. One is 100x objective and the other is a 50x objective. The reason of which I will be discussing in my subsequent slides. The results for 100x objective is shown by these, the red dots, whereas the black square shows the results obtained from the 50x objective. The slope of, the G peak shift as a function of power for 100x objective was higher than that of the 50x objective, and it is obvious because the incident laser energy density is high. One observation from these set of results is the G peak shift as a function of temperature or power always had higher, slopes than that of the mechanical exfoliated graphene. So that sort of raises many questions which needs to be answered by, determining thermal conductivity and total interface conductance of the film. Another interesting observation, when we transferred these grown films onto silicon dioxide substrate, it always contained wrinkles in them, even when the thickness was quite high, say around 15 nanometer. Around this thickness regime, say the bending rigidity of the film doesn't allow the formation of wrinkles in them because the bending rigidity varies as a cube of the film thickness, and around 15 nanometer, it doesn't allow the formation of wrinkles. So we attribute this, visible wrinkles in our sample to the presence of stacking faults. And we thought it would be interesting to even study, these thermal properties at these local sites, at the local wrinkle sites. And we similarly carried out the similar measurements at these wrinkle locations. And now, in order to obtain the thermal conductivity and total interface conductance for all these three cases, we need to solve for these heat diffusion equations along with the following boundary conditions. It can be done by analytical technique, or it can also be done by using a numerical technique. We chose a numerical technique, which is called finite element simulation technique. And we solved this heat diffusion equation, where the first equation is a equation representing the radial temperature distribution in the film, whereas the second equation represents the radial as well as the distribution of the temperature in the z direction. Out of all this, what we obtain is the temperature as a function of the radial coordinate. But at the end, in order to compare this simulated temperature rise with the experimental temperature rise, we need to obtain the average temperature rise, for the radial temperature distribution of the film, which is Gaussian in nature. Now, this formula is what can be used for the calculation of this average temperature rise. Now this average temperature rise in this figure A is plotted as a function of thermal conductivity and total interface conductance for 100x objective. In order to obtain a thermal conductivity and total interface conductance values, we need to compare these results with the experimental temperature rise value. The shaded region over here shows experimental temperature rise for 100x objective at a given particular incident power. And as you can see over here, this temperature rise is associated with infinite combination of K and G values. So in order to obtain a unique value of K and G, we need to consider the temperature rise with respect to another objective also, which is here a 50x objective. And this is the reason why we chose two different objectives in our power dependent measurements. We also obtained the temperature rise ratio with respect to two different objectives. And the experimental temperature rise ratio is shown in this figure. In order to obtain this unique value of K and G, we need to consider these two shaded regions and find the intersection between them. And for all the three cases, this table sort of gives all the obtained results. And for mechanically exfoliated graphene, the value of thermal conductivity and total interface conductance are in very well agreement with the literature. Whereas for the CVD grown graphene at the flat regions, at the unwrinkled locations, the thermal conductivity is found to be reduced by 2 to 3 times. And we attribute this decrease in thermal conductivity to presence of rotational stacking faults in our sample, as it is already established that for bilayer graphene with rotational stacking faults or stacking disorder in them, the value of thermal conductivity decreases. And that is due to this formation of Moire patterns because of which the size of the unit cell increases and hence causes a consequent decrease in the size of the Brillouin zone in the Fourier space. And because of that, there is a large number of folded phonon branches that appears in a reduced Brillouin zone, which causes an increase in the phonon unclav scattering and a reversal of phonon direction of the phonon momenta. And that causes a decrease in the thermal conductivity here. But what we observe at the wrinkle sites is quite interesting, that the total interface conductance has gone down by 1 order in magnitude. We attribute this decrease in the total interface conductance value to loss of thermal bonding between the film and the substrate at the wrinkle location. It is due to the local delamination of the film from the substrate. And that sort of causes a decrease in the total interface conductance value. But what we observe for the value of thermal conductivity is quite intriguing. There is an increase in the thermal conductivity value, whereas in the literature it was always shown by various groups that at the wrinkle sites there is a decrease in thermal conductivity due to various effects like phonon localization or increased phonon scattering or reduced phonon groove velocities. But in order to explain these observations, in our case, it is to note here that the curvature of the wrinkle studied in our case is lower, and hence wrinkle doesn't contribute completely in the reduction of thermal conductivity here. Whereas this increase in thermal conductivity in our case is attributed to local uncoupling of these rotational stacking faults in our samples. And that sort of causes an increase in thermal conductivity due to restoration of the size of the Brillouin zone locally. And with this, I would like to conclude my talk with the following conclusions: that thermal conductivity of CVD fuel graphene with rotational stacking faults was found to decrease, which is attributed to enhanced unclav scattering. A remarkable wrinkle-mediated uncoupling of the misstacked layers was observed with partial restoration of thermal conductivity. And a decrease in total interface conductance in the wrinkle location was observed due to reduction of thermal bonding between the film and the substrate. Thank you.
Thank you, Dr. Mohapatra, for the interesting talk. Now the talk is open for questions and comments.
Sir, can I ask one question?
Yeah, sure. Yeah, please go ahead.
Yes, ma'am.
Yeah, hi, Akash.
Hello.
So yeah, lot of work.
Thank you.
So one question is, of course, this you presented in a very short time, so a few things I just missed, or maybe I just need to go through the paper. So, what about the so when you were comparing, so are the number of layers in all three cases are same?
In case of mechanically exfoliated graphene, the thickness is around 9 nanometer, whereas for the other two cases, yes, they are in CVD grown graphene cases, they are same.
So they are nearly same, or they are same?
Yeah, they are nearly same. Yes,
they are nearly same. So, and then what about the substrate? Are you using same substrate, silicon dioxide or something like that?
Yes, it is a same substrate, silicon dioxide being used for all three cases.
So after when you grow CVD, grow in CVD, these graphene, you grow on some different substrate, and then you bring for the study, you bring to the different substrate, is it?
Yeah, we grow on nickel substrate, and then subsequently we transferred it to onto the silicon dioxide substrate.
So this wrinkling is not really a very normal procedure, means normal, not the procedure, normal phenomena in graphene when you, because these substrates are different and you know the
yeah, you are right. But
mismatch and thermal conductivity, a lot of differences are there in their properties itself. So I wonder if the speculation of, because I didn't see in TM also very clearly about those stacking fault and other defects which we were talking about. So probably you might have done something else also to verify all these studies, but that's what I just kept wondering about, the differences, what you are getting. So if the experimental error is just taken care.
Yes, I mean, these regions that I mentioned, otherwise, this won't be a region or the contour region that I have, mentioned in this over this KG plane. Otherwise, this, if I just consider the experimental temperature rise, this will be a single line. But after considering the errors in the experiment, this becomes a contour region as shown in the figure A here. And that sort of, gives us a value that we have reached in the conclusion, and with the included with the error bars. Those are mentioned in the paper. Maybe you can just visit the paper.
Yeah, sure. Thank you.
Thanks.
Okay, any other question? Okay, no more question. Let us thank Dr. Mohapatra once again.
Thank you.
I will move to the next speaker. The next speaker is Dr. Shaila Kumar Sethi.
Yes, sir. Yes, sir.
He's from CSIR Institute of Minerals and Materials Technology.
Yes, sir.
He's going to talk on influence of 1 minute. So influence of substrate temperature on the growth of doped nanocrystalline diamond thin films. So I invite Dr. Sethi to give his talk.
Thank you for your kind introduction, sir. Firstly, I would like to thank the organizing committee to giving the opportunity to present my ongoing work. I am Shaila Kumar Sethi, pursuing my PhD under CSIR, Institute of Minerals and Materials Technology, Bhubaneswar. Today, my presentation is on influence of substrate temperature on the growth of boron and a nitrogen doped nanocrystalline diamond thin film over the silicon substrate. So these are my contents. In an introduction, we'll discuss various properties of the diamond. Then we'll see how the nanocrystalline diamond thin film over the silicon substrate. Then we'll discuss about the motivation part. Then we'll discuss about the fabrication of the nanocrystalline diamond thin film. Then we'll discuss various characterization techniques. Then we'll discuss about the micro illumination plasma display. Then we'll discuss about the conclusions. So this is the crystal structure of the diamond having coordination number 8 and 4 atoms present in each body diagonal at 1/4 and 3/4 position, which is face-centered cubic in nature, with having lattice constant of 3.567 Armstrong and bond length of 1.54 Armstrong. As we know, the diamond is the hardest material found on Earth. Due to the presence of sp3 phase, it has high density, which is around 3.52 gram per centimeter cube, and the diamond has a thermal conductivity, high thermal conductivity, which is 5 times more than copper, and also the wide band gap of 5.47 electron volt with high resistivity, which is greater than 10 to the power 16 ohm centimeter. Then we'll see how the nanocrystalline diamond thin film grown over the substrate. So this is the schematic diagram of microwave plasma enhanced chemical vapor deposition systems. This is the quartz tube. Inside the quartz tube, microwaves and gas molecules are allowed to pass inside the chamber. When the microwaves are collided with the gas molecules dissociate into ions, and that ions form a plasma, and that plasma deposited over the silicon substrate. Then we will get the diamond thin film. Then this is the typical structure of the microcrystalline diamond thin films, which is grown in the presence of methane and hydrogen plasma. Its drawback is it is highly insulating in nature. When we dope with some dopant like nitrogen, boron, and phosphorus, that shows the diamond thin films the electrically conducting in nature. My aim is to synthesize the electrically conducting nanocrystalline diamond thin film in the presence of methane, hydrogen, nitrogen divergent plasma by varying the substrate temperature from 400 degrees Celsius to 850 degrees Celsius. Then I would like to investigate the change in morphology, then change in microstructure, and the change in phase with respect to the substrate temperature. Then we'll discuss to achieve high plasma illumination for better conductivity of nanocrystalline diamond thin films. So what are the conditions of growth? We have taken the microwave power of 3000 watt having pressure of 120 torr, growth time 30 minutes, and we have varied the substrate temperature from 400 degrees Celsius to 850 degrees Celsius to get the diamond thin films over the silicon substrate. Here you can see at 400 degrees Celsius the grain sizes are bigger. When the substrate temperature increases to 550 and 700, the grain sizes decreases. And when we tune the temperature at 850 degrees Celsius, we are getting nanowire like structures. And these are the pictures. The inset pictures are the cross-sectional same images. From these scanning electron microscope images, I have calculated the grain size. When the substrate temperature increases, the grain size decreases. After 700 degree, it is increases. As well as I have calculated the growth rate. When the substrate temperature increases, the growth rate increases, then decreases. In case of 700, it is the grain size and the growth rate changes. It is due to the incorporation of nitrogen at higher temperature. Then by using atomic force microscopy, I have calculated the surface roughness, which is when the substrate temperature increases from 400 to 850 degrees Celsius, it is decreases then increases, which is consistent with the grain size and growth rate. Then to check the change in phase, I have characterized the diamond thin films by using Raman spectroscopy in UV region of laser wavelength 325 nanometer. Why I have chosen in UV region? Because in UV region the sp3 is more sensitive in the UV region. So in the Raman spectroscopy, I have observed 4 peaks, that is diamond peak, then D peak, diamond peak due to the crystalline structure of the diamond. Then D peak due to the presence of the defect, means in D peak sp3 and sp2 materials are there. In G peak it is maximum number of sp2 graphitic materials are there. In case of new peak, it is due to the presence of the transpolyacetylene peak material, or you can say the presence of the CH bonding. From this Raman, we have calculated the diamond quality factor by using this equation. You can see when the substrate temperature increases, the diamond quality factor decreases, and when the substrate temperature increases, the crystal size decreases, then increases. By using this formula, I have calculated the crystal size, and this crystal size more consistent with the same scanning electron microscope grain size. Then I have characterized the same Raman study in the visible region. Why I have taken them in the visible region? Because in the visible region, the graphitic band is, the graphite is more sensitive. That's why I have taken the Raman study in the visible region. So here also same peaks are obtained: diamond peak, D peak, G peak, and new peak. From this peak, I have calculated the G band full width half maxima. When the substrate temperature increases, you can see the G band full width half maxima decreases, and the G peak also I have calculated G peak position. You can see when the substrate temperature increases, the G peak becomes narrower, and it is shifted towards the right side. Sorry, a higher wave number. It is due to the change in phase from sp3 diamond phase to sp2 graphitic phase. Also, I have calculated the ID by Ig curve. Ig, when the substrate temperature increases, the ID by Ig ratio increases, because when the substrate temperature increases, we are getting the defective, means more sp2. sp3 is converting to sp2 more here. That's why the ID by Ig ratio increases. I have calculated ITPA by ID plus ID Ig. From this graph, you can see from this graph, when the temperature increases, substrate temperature increases, the new peak, the transpolyacetylene peak, become decreases. This one, the trending, the same thing. From the Raman, I have got the information, the conversion of phase from sp3 diamond to sp3 graphitic phase. Then for the confirmation of sp3 to sp2 phase, I have characterized the diamond thin films by taking the X-ray photoelectron spectroscopy. Here you can see the phase change occurs from the sp3 to sp2, and also this one shifted towards lower binding energy. Here it confirms the phase change. Also, why the phase change occurs, you can see this is the present incorporation of nitrogen at higher temperature. That's why the sp3 phase converts to sp2 graphitic phase. To investigate this one, to confirm the sp3 to sp2 phase, I have taken the images of transmission electron microscope images for the nanocrystalline diamond thin films or the 850-degree diamond thin films. So this is the bright field transmission electron microscopy. This is the SAED pattern. From this one, we have taken this one, and from here you can see the rings are which is 111, 222, 33, 311, due to the presence of the diamond phase, and the black spot in the middle black spot due to the presence of the graphitic phase. And also we have taken the dark field transmission electron microscope image due to the for the confirmation of the presence of the diamond and graphitic. You can see the yellow nano wire-like structures are formed, and the graphitic phase are surrounding to the nano wire structure. Then due to the presence of sp2 graphitic phase, which is conducting in nature, we have characterized the samples by Hall measurement system. So what is Hall effect? When a current carrying conductor is placed in a magnetic field, and EMF is induced in it. When that EMF is perpendicular to both direction of the current and as well as magnetic field. If we will place the samples, suppose this is the samples 1, 2, 3, 4 of the corners. If we connect the 1, 2, 1 and 3 corner in the current source and voltmeter in the 2, 4, then from this one and this one we can calculate the Hall coefficient. Similarly, if we will connect the current source in between 1 and 2, voltmeter between 3 and 4, we can calculate the resistivity. From the Hall coefficient and resistivity, we can calculate the electrical conductivity, mobility, then seed carrier concentration. Then from this Hall measurement, I have checked the conductivity. When the substrate temperature increases, you can see the conductivity increases. To carry out this one, I have changed the Hall temperature from the room temperature to 300 degrees Celsius. You can I got the same trend as the electrical conductivity increases with the substrate temperature, and we are getting the better conductivity at 850 degrees Celsius diamond thin films. Also, I have calculated the mobility. When the substrate temperature increases, the mobility decreases. To check this one, I have changed the Hall temperature from room temperature to 300 degrees Celsius. Here also we are getting the same trend. When the temperature increases, the mobility decreases. Also, I have calculated the seed carrier concentration. You can see the higher seed carrier concentration is more in case of 850 degree nanocrystalline diamond thin films. So from the Raman, Hall, and Tame, we have the diamond thin film show the conducting properties. So we can use the diamond thin films as a cathodic device. So in microplasma display device for plasma illumination. So this is a chamber. Inside the chamber, I have taken this is the diamond nanowire, the thin film, which is connected to the cathode, and this is the ITO coated glass which is connected to the anode. In between the ITO coated glass and diamond nanowire, one spacer is there. In the spacer, I made a hole to create the plasma that is around 0.25 mm. So you can see the plasma illumination what I have measured from the microplasma device, and in case of 850 degree Celsius nanocrystalline diamond thin films, I got the threshold voltage of 330 volt. And but in case of lower substrate temperatures, we are getting the plasma illumination, but as compared to 850 degrees Celsius diamond thin films, it is higher threshold voltage. And in case of 850 degrees Celsius, the plasma illumination is more as compared to the 3 substrate temperature diamond thin films. To confirm this one, I have plotted the graph between plasma current density versus voltage supplied, and we have obtained the same graph for the 850 degrees Celsius. We are getting the low threshold frequency, low threshold voltage. And from this, what we got, the better electrically conducting NCD films leads to high intensity of plasma illumination. And this plasma can be used in various way. So this plasma can be used for the plasma display, for the plant display, and also can be used as a plasma torch for wound healing, for the cosmetics we can use. Lastly, I would like to conclude here what we have seen, the origin of one-dimensional diamond nanowire film grown at 850 degree nanocrystalline diamond thin films. And from the Raman study, we have seen the phase change from sp3 diamond to sp2 graphitic phase. And from the XPS and transmission electron microscope studies, the presence of sp2 due to the presence incorporation of nitrogen in the growth plasma. And from the Hall measurement studies, high electrical conductivity for the diamond nanowire films grown at 850 degrees Celsius nanocrystalline diamond thin films. And from the microplasma device, we have seen low threshold voltage at high intensity plasma achieved in the microplasma display for diamond nanowire films. Lastly, I would like to acknowledge ACSR, CSR IMMT Bhubaneswar, and Gdansk University of Technology, Poland. Thank you for your kind attention. Thank you, sir.
Okay, thank you, Salil, for your interesting talk.
Thank you, sir.
The talk is open for questions and comments.
Yeah,
sure.
Okay, I think Padmanabh is asking something.
So can I ask her, Sangeeta, you want to continue?
No, please continue.
Yeah, so thank you, Salil, for a nice talk.
Thank you, sir.
And I'd like to ask that you have mentioned B2H6 in the growth process. So are you using B2H6?
Yes, sir. Yes, sir.
Why it is required?
Actually, sir, from this hydrogen, initially the hydrogen we need to etch the non-diamond component. We need this one, and boron also needed to the electron to move from the nano inside the nano wire to the boundary boundary of the boundary of in the grain boundary, from the inside the nanowire to the grain boundary. It helps to transfer the electron from the from the inside core to the outside grain boundary to help the conductivity, sir.
Okay. So since it is a dangerous gas, so I think what kind of precautions you are taking?
Sir, we are placing this cylinder outside the chamber actually, and we have connected the pipe inside the lab through a long distance.
Okay, thank you.
Thank you, sir.
Just one question. So isn't the result quite intuitive? I mean, you are making the thing very deep. I mean, you're doping the system, first of all, you're going to 850 degrees centigrade, isn't it? So
yes.
it's becoming, so the change in conductivity, what you see, is
yes.
Isn't it very intuitive?
When actually
that's what you would expect, right?
Yes, ma'am.
Because you are saying that when you are doing the growth at 850 degrees centigrade, you have nitrogen which is getting doped, right?
Yes, ma'am.
And in fact, you are also getting an increase in the defect density. That's what your Raman says.
Yes, ma'am.
Okay.
And actually nitrogen, it is more heavier than hydrogen. That's why nitrogen is active at higher temperature. After
okay.
Yes, ma'am. That's why it is showing nanowire-like structure.
But the morphology is not really playing a major role, I would say, or is it? It's mainly the doping which is changing the conductivity.
No, ma'am. Actually, the phase change occurs because from the sp3 to sp2, actually, when the temperature increases, the phase change occurs. From here, you can see the phase change occurs. Actually,
yeah. So that is also one of the major reasons why you're making it more conductive.
Because of the presence of the sp2.
Exactly.
Yes.
That's what I'm saying. This is quite intuitive. I mean, you would expect that when you have the phase change, it becomes more conducting, and that's what you're seeing. But of course, the final result which you show about the plasma, the lowering of the voltage, that is very interesting.
Yes, ma'am.
So
actually, I have made this instrument in my lab, ma'am.
Yeah. Good work. Thank you.
Okay, thank you, ma'am.
Okay, can I ask one last question? Have
Yes, sir.
you prepared many samples and measured this Hall effect, etc., conductivity measurements?
Yeah, actually, for the four samples,
Okay.
4 samples I have measured.
Okay, so they are reproducible essentially, by
Yes.
and large. Okay.
Yes.
Good. Okay, so let us thank Salil for the interesting talk once again.
Thank you, sir. Thank you so much.
And, I think this was the last talk, if I'm right.
Yeah.
Okay. So,
May I leave, sir?
yeah.
Yeah, you can.
Sure.
Okay. Thank you, sir. Thank you, ma'am.
So we thank all the speakers for their very interesting talks, and I hand over the session to Dr. Sangeeta now.
So thank you, Professor Nigam, for kindly chairing the session. And I would like to thank all the speakers once again. So this was basically this on growth, and we had very interesting talks covering the growth processes of thin films, carbon-based materials, as well as the lateral heterostructures and even this vertical heterostructures. Okay, so we'll meet again at 2 p.m. So lunch break. So see you again after lunch. Thank you. So
Okay.
is Ruchi there? Or we would like to, she wants to check.
Hello? Hello, am I audible?
Yeah, you are,
Yeah, I'm just sharing my slide.
Yeah.
By the way, is Dr. Prasanna Nagarajan around? I think he's left probably.
Yes, I am around.
Ah, he's there. Okay.
You are on screen, right?
I have shared my slide. Is it visible?
Yeah. Can you just hold to 1 second, sir? We'll just see her slide and we will.
Yeah.
I'm checking the slide. Is it
Yeah, everything is fine. Okay, thank you, Ruchi. Yeah.
I'll just stop sharing.
Yeah.
Yeah.